UCFER Annual Technical Review Meeting. My name is Omer Bakshi, and I am the DOE Project Officer for the University Coalition for Fossil Energy Research. If we could go to the next slide. So the first thing I want to, I guess before we get started today, I have some DOE security requirements to fulfill by telling everyone here this meeting is considered open to the public. That has a specific meaning for DOE to include both our federal employees and members of our site support contractor community. It means the purpose of this meeting has been examined during the planning stages, and NETL has made some specific determinations that affect our attendance. All information presented at this meeting must meet criteria for public sharing or have already been published and available in the public domain, or expects the material to be made available soon after the conclusion of the proceedings. Please do not communicate information that is considered official use only, proprietary, sensitive, restricted, or protected in any way during the presentations or during any sidebar or casual conversations. Because foreign nationals who may be present today have not been approved for access to DOE information and technologies. So for NETL personnel here today, the open to the public designation does not remove your obligation for personal reporting if warranted. The usual rules apply in that regard. So that being said, I want to turn everyone's attention to the agenda. If you look at the side panel on your webinar screen, there should be a tab that says handouts. It's on my screen, it's between questions and chat. If you expand the handout tab, you should be able to see a copy of the meeting's agenda. Prior to your presentations, there will be a break during which we will ask you to perform a mic check. We had some individuals just do that now for this upcoming slate of presentations. So just be aware that we will be asking you to unmute yourself and make sure your audio is coming out okay. In terms of presenting, there will be each individual will have 20 minutes. Please try to adhere to the 20-minute time frame. You will be given time warnings 5 minutes in advance and 1 minute in advance. So these time warnings will pop up on your chat window. So please have your chat expanded and keep an eye on it during your presentation so that you can be mindful of when your 5 minutes is up and when your 1 minute is coming up. So be mindful of that. And as for the Q&A procedure, we will not have Q&As after individual presentations for the most part. Q&As, if you turn your attention to the agenda, will be held after all technical presentations are given under a specific technology area. So if you would like to ask questions, you have one of two options. You can either submit questions through the question tab. If you are an attendee, you will be able to ask a question through that tool. If, however, you are designated as a staff member or a panelist, then please submit your questions through the chat box and make sure everybody can see the question, or at the very least, make sure all panelists can see the question. If you prefer to ask your question verbally, make sure you at least type it out first and then raise your hand during the Q&A session so that we can unmute your mic and hear you verbalize your question if it's more technical or more nuanced. So that is all I had to say in terms of the nuts and bolts. If we go to the next slide, I just want to give a quick shout out, acknowledgement to the people who make UCFER and this meeting possible. So if we could go to the next slide. On the NETL side, we have, or excuse me, on the Penn State side, we have the operations management team led by Bruce Miller. He is the PI for the University Coalition. Under him, we have Elizabeth Wood, Kelly Rhodes, Jennifer Lear, and Jennifer Matthews. For NETL support, I want to acknowledge Lauren Timko as the key site support contractor for all things admin UCFER related. I want to acknowledge Sham Madhaba. He is the DOE Technical Project Officer for Coalition. Karen Blaney for handling the registration side of things, and Justin Solly, who is the man behind the scenes for this webinar, trying to make things work as smoothly as possible for everyone. So I'm going to transition directly to Dr. Sean Plasinski of NETL, who will deliver some opening remarks for everyone in attendance. So let's get Sean's presentation up, and Sean, the floor is yours.
Thanks, Omer. Glad to be here with you again today on the second day of the UCFER Technical Review Meeting. I am the Deputy Director and CTO for NETL. I am also the Executive Director of the Technology Development Center at NETL. And this center is responsible for the project management of the external projects for the programs we execute for the DOE offices of Fossil Energy and Carbon Management, Office of Electricity, CSER, and parts of EERE. Yesterday, our director, Dr. Brian Anderson, gave a nice overview presentation of NETL, our mission and vision, and described our strategic initiatives and key laboratory initiatives. This is followed by another excellent presentation by Dr. Bruce Miller, director of the UCFER, who provided a nice overview of the history and awards that came from the program, along with some very impressive impacts and accomplishments. And I just want to build a little bit more on those this morning. Back up one, Justin. I remember back when the UCFER concept was conceived about a little over 7 years ago at NETL. The main driver was, how can we engage the core competencies we have with our on-site research efforts at NETL and engage the university community for collaborative efforts in support of the fossil energy research work we're doing. Sounds like something easy to do, but it was anything but that. It was really not straightforward due to some limitations we have as a federal agency and the fair competition, et cetera. But we overcame this, and with the collaboration of the universities in the program, have shown what can be done collaboratively. As Bruce said yesterday, the coalition consists of 15 universities with a variety of fossil energy expertise. You couple that with the research competencies that NETL has to offer, the collaborative results and impacts are significant. A National University Alliance of Fossil Energy Research came about with the major collaborative efforts with NETL to address specific topics in NETL's R&D mission space, resulting in 43 projects, 237 participants, 10 credas, 34 journal articles, 23 conference papers, and over 100 presentations and posters, and even 3 patent applications. These results came about from the collaboration and a diversity of thought obtained by the 15 universities and NETL research staff. Definitely a great outcome. I just want to take the opportunity, as Brian did yesterday, to express NETL's appreciation to the universities in the UCFER and recognize their importance in contributing to NETL and the Office of Fossil Energy and Carbon Management mission in obtaining our goals and objectives. It has been mentioned numerous times the past couple of days about the collaborative efforts, which led me to place on the slide a quote from Steven Anderson, alone we are smart, together we are brilliant. I think this phrase really sums up the impact that's been realized from the UCFER NETL collaboration over the years. Next slide. I also want to expand quickly on a couple of slides Brian presented yesterday. From the NETL snapshot slide, I just wanted to point out the 1,000+ R&D projects in 50 states with a $5.2 billion total award value. These are projects that are managed by the Technology Development Center at NETL that I mentioned at the start. And it's part of external projects we manage for FECM, OE, CSER, and parts of EERE. Next slide. We help develop and execute dozens of funding opportunity announcements, or FOAs, through the course of a fiscal year. The NETL budget was around $1.1 billion. Of that, approximately 70% of that flows to projects either underway or for new work selected through the competitive FOAs. Next slide. as you can see from, actually, I should have left the last one on, but that's fine. You see the significant portion of funding is in the fossil energy area, but a good portion of the funding, around 30%, was in programs we execute for other parts of DOE, OE, CSER, and EERE. Now, Brian mentioned yesterday our core competencies that have been engaged through UCFER, and those were the first 5, really, the computational science engineering on through strategic systems analysis. The 6th core competency at NETL is that of our program execution and integration and project management. As I mentioned, we execute FOAs for various parts of DOE. The technology thrust lines here on the slide show the various areas that we manage. For DOE's Office of Fossil Energy, we handle all the programs from carbon capture and storage, advanced energy systems, supercritical CO2 power, rare earth elements, all the natural gas, infrastructure, unconventional resources, methane hydrates. But we also handle handle all the parts of Office of Electricity and Cyber for the other parts of DOE. And then for EERE, the vehicles, buildings, and parts of geothermal and advanced manufacturing. Next slide. The reason why I wanted to highlight these items in the past slides is to make you aware of opportunities NETL has in potential upcoming FOAs or other areas to build upon the success of work that we've done in UCFER to help further NETL meet its missions and goals. On the slide here, I have listed links where you can find all the solicitations and FOAs, prizes and challenges, and another link, third link, on other opportunities to partner with NETL. I also included a 4th link here on an opportunity to obtain laboratory equipment it's energy related that you can receive through a grant program. It's listed on our business page, but the actual link that you would need to get to for the program itself is listed second there. I just hope you can check out these other opportunities to work with NETL and potentially further the good work done by UCFER in these areas. And last slide. Finally, I just want to again say thank you to Bruce and his efforts in UCFER and all those at Penn State involved with this. All the UCFER universities have contributed to NETL meeting its mission, and all those at NETL involved with the program, Omer, Sham, for all your efforts you've done in making this program a success. With that, I'll turn it back over to you, Omer, to continue with the program today.
Thank you so much, Sean. That was a great overview. Before we jump into our first presentation for today, I am actually going to hand it off to Bruce Miller, the PI for the University Coalition for Fossil Energy Research, who will be introducing speakers as they come up. So Bruce, I'll hand it over to you and we can get the first slides up. Thanks.
Okay, thank you, Omer. Yeah, the next 3 presentations are in the area of cross-cutting research. And 2 of these have recently started in round 6, and 1 is finishing up this month in round 4. The first presentation will be by Wei Zhang and Santanu Paul from the University of Pittsburgh. And go ahead when you're ready.
All right, hope you guys can hear me. Thank you very much. So this is a long title for our project, but basically, we are studying the wire arc additive manufacturing for the steam cycle components, focusing on location-specific design using the combination of high-throughput experiments and the machine learning. So this is a project where I collaborated with Albert Tu in our same department at University of Pittsburgh, and also we involved different industry partners, including Siemens Energy, Jeffrey Tech, and Haynes International. So basically, Siemens Energy will be able to provide us some guidance later on once we manufacture some of the related geometry close to the component prototype, and Jeffrey Tech is helping us to developing some of the recipe for the printing as well. So for the Haynes, they supporting us with the study of Haynes 282. So right now we are focusing on studying Haynes 282 alloy in this project. Next, thank you. So this is the overview. I think everyone works for this fossil fuel energy and coal power plant. You're probably familiar with some of the urgent need of ultra-high temperature critical employment for these advanced alloys. So basically, we are targeting the performance at the high temperature around like 750 degrees C, and pressure would be this range. And we expect the efficiency will be significantly improved with reduction of the emission of carbon dioxide. Next. Next, please. So, yeah, there are a little bit lag. Yeah.
Yeah, bear with us.
It's fine. All right, so this is the overview for this table. We have challenges. We already did one of the project about WM process with recent technology. We understand some of the technical challenges here. So in this one, we thinking we should be doing a little bit more with a location-specific design. And right now we focusing on doing some of the simulation, understanding the residual stress and also the high throughput experiments and machine learning. Well, hopefully we can do some demonstration on how to utilize machine learning to help with WAM process. So we are focusing using the Tech machine ARC 605 to produce these samples. Next. So this is a system design chart for the Haynes 282. Basically, these are the different steps on the left, talking about process. We're starting from the wire composition of Haynes 282 and melt the wire using the arc and do the homogenization with the solutionizing and agent. So we do have different unit of the microstructure. We're talking about matrix FCC phase. We want to control the grain texture, grain size, and homogeneity. Of course, everyone probably can expect the WAM process have a large component, so usually they have a very large columnar structure. So we have two extremes. One is very much refining the grains and how to utilize in the residual stress. That's the reason why our tools group is working on that. For the precipitation, we're talking about nickel titanium 3 aluminum precipitation with L12 structure, and we have some complex carbide involved. We also expect long time employment of the material probably will show up some of the detrimental phase as well. We try to avoid. As printed microstructure is certainly very important, so we'll do some of the design for the grain texture and refinement. For the properties, ideally we want to get in the uniform property at the different locations and also showing the similar performance with the raw material. Next. So this is the kind of overview. So we will have the 3 different bullet points highlighted as a red star. So as printed microstructure at the moment we're starting, and the recrystallization study at high temperature, we're trying to do some optimization. And we also do the agent study. I have to emphasize, before we go to the location specific, we want to making sure that we understand the bulk without location specific, how it runs. And the location specific also, depending on the processing parameter, that's a kind of different combination. Before going there, we have to making sure, and we also need to calibrate our ICME modeling. So basically, A and B are the 2 types of the alloy component we are trying to study, and B component would be related to the location specific we are expecting. Next. And then we're using 2 different printing strategies. So we have one left zigzag and the right is a single bead. As you can see, the printing strategy is different. The one zigzag is usually, printed through the paths where you have small area sections, and the single bead usually, print with a larger component with a circle and so on. Next. If you haven't really thinking very carefully in detail practically, you probably thinking about, oh, we need to design different printing process, different printing parameter, trying to study the location specific. Actually, I think this is very tedious. We have to be realizing the limitation of material science is actually lack of data. We don't have a lot of data, so we don't want to be in an ocean generating the data. That's not practical for this 2-year project. We want to demonstrate the way how to do something moderately. So investigating these 2 different patterns, we actually can utilize and minimize the efforts of changing a lot of processing parameters, but still keeping away where we see some of the difference of microstructure. At least right now, this is what we learned after taking over this project. I have to say these 2 big images of the microstructure has to swap. I made a mistake once I prepared the slides. So basically zigzag showing a kind of parallel with the fusion line, whereas the single bead showing with you know, the distorted fusion line and the indication of the multiple. This we are looking at the cross section along the XZ plane, you can say. Yeah, next. So this is a little bit more closer looking. So this green color with yellow one are the hardness mapping that we did. So as you can see, these 2 microstructure really introduce a difference regarding the hardness. And certainly we are expecting there will be some differences also related to the heat treatment response and the performance later on if we evaluate the microstructure. And meander zigzag shape printing pattern, you can see a lot of like columnar, very straight, very large structure with the grain, and a single bead actually consistent with the observation of the optical microscopy. Next. And so this is a sprinted one. So this section we're talking about recrystallization. So we're evaluating recrystallization because different process will launch different microstructure response. So we did a heat treatment at different temperature, high temperature. We think that residual stress will be able to promote the recrystallization, but then we don't know the level of the residual stress for this process. This is a 1200 degrees C. You know, ideally we should flip and see the difference and go back. But then let's go next. The first line is you can go next. The first line is a single bead, and the second line is a meander. And then we do 1 hour, 2 hour, and 4 hour. If we see the next slide with the 1250 degrees C, you start to see some of the recrystallization a little bit more pronounced in the single bead, while in the meander is not that significant. Next. So next slide will be the 1300 degrees C. So we get enough time to digest this microstructure. 1300 degrees C is showing up, hopefully. Next slide, 11.
Sorry, it's taking a minute.
Yeah. Yes, as you can see, if look at the top on the, now it's 13 degrees C. As you can see, the same microstructure, right? So experience a different heat treatment, you start to see this black dots. What that? That's a pore. So we're actually, heating at the temperature where you start to see overcrust incipient melting. That's a reason. So therefore, the best option that we have is probably 1250 degrees C. And certainly we see the difference regarding the single bead and the meander. And the single bead is probably much better with refined grains. Next. So I think the next slide, we will be showing the experimental procedures. Basically, the Haynes 282 will have 3 different heat treatment sections. The first section you can consider as a homogenization. It will be 1150 degrees C for 2 hours with water quench. And then the second and third will be considered as agent step. So first agent step usually we consider as helping the carbide precipitation. If you really use a Calvert calculation computation, depending on which database you use, but then we use a TC nickel database, Samocat. These does only show the carbide as MC carbide. And then at lower temperature at the third section with the agent 2, you would heat treat it at 788 degrees C, 8 hours. So this will be experiencing the gamma prime precipitation. And actually here we're also expecting the M23C6 carbide showing up. Go next. And then, so this is you know, the observation of the carbides. So the as printed one on the top, you can see the, you know, consistent with the shell simulation. Basically, MC carbide usually experience a little bit higher coarsening rate. It's not kind of strange. You will see the MC carbide. And then solutionizing at 1150 degrees C, you see the MC carbide. But then later on, the first agent 2 hour, you see the mixture, these two carbides, and the third stage 8 hours, 788. You also see this. And then the morphology changing a little bit. And M23C6 is good for the creep resistance. Next, yes. And here we did a lot of TM study because our idea is since MC carbide and 23C6 carbide are very sensitive with titanium. Titanium is also kind of, you know, partitioned to the gamma prime precipitation, so we want to making sure that we have a good understanding at this level. Next. So the next slides, we're talking about like a gamma prime precipitation. Before we introduce gamma prime precipitation during the heat treatment, we also, you know, studied the as printed microstructure with the TM. I have to claim that not everyone will study TM at the as printed microstructure, but we did find very interesting phenomena. So this has been confirmed. We do see the gamma prime precipitation in as printed microstructure. We talked with Haynes. I don't think Haynes expert seen this before during the welding of these alloys. You know, this is a different heating history introduces different microstructure. Go next. Maybe it's not necessary say how critical of this as printed microstructure is a gamma prime, but let's keep thinking about this. If in the future, maybe near future, if someone want to have minimize heat treatment and introducing gamma prime during the as printed microstructure, will be going to be very critical. And of course, it will involve a lot of like optimization of the processing as well. So this is a gamma prime heat treatment. We, as I already mentioned, we have to calibrate our ICM model. Therefore, we utilizing the recommended recipe for the heat treatment for the cast alloy. And we do confirm all of this precipitation. We want to quantify them and then supporting our TC Prisma precipitation kinetic simulation next. And then we also did investigate another different temperature, 800 degrees C for 6 hours. Very interestingly, that's also new to during our discussion with a Haynes expert. This is a kind of alloy that you know only have a very small temperature difference, but we see this gamma prime is very refined microstructure. As you can see, this is we're talking about like the scale of 3 to 5 nanometer. Next. So we are unclear about this. This is some of the new observation during our research. We certainly were moving forward and take a closer look once we get a more alloy study. And then I think ICME model, then we are also talking about the machine learning. So next, how to link with machine learning, we need to making sure we have a data bank to support machine learning. So this is kind of, you know, the table that's showing what are the things that we will consider in the machine learning data bank next. So we have the ICME framework building up. So basically, we want to have the ICME model be able to predict the yield strength and the hardness. Hardness is easier. And next, so we develop a kind of yield strength model according to the literature collections, and these are the detailed model map talking about different contribution to the yield strength next. And we do have a kind of relation between the yield strength and hardness we want to utilize because we can do hardness mapping. So in this project, we were focused on the room temperature and of course supporting all of this measurement. We calibrate using the published data of the casting and rod. Next. I have to say we have been talking with Dr. Chantal Silbrak, and we have launched an agreement. Maybe later on we can use NETL facility to test with a high temperature ES-trans model and high temperature hardness. So we can support in all of this model study. So next slides showing the comparison that we use the calibration according to the cast alloy, and then this is comparison. I have to say the agreement is very good at the high temperature. Next. So this part is related to the residual stress modeling. So this is also another part we later on want to have a kind of idea and how to approach with the machine learning enhanced modeling. I've let Centennial, he's a postdoc of Albert too, giving this part. So only several slides. Yes. Centennial, can you speak?
Yeah, for the, can you go back to the previous slide, please? So we have developed this framework. We did develop a detailed thermomechanical finite element analysis of a complex shape so as to get the temperature field, the stress field, and the melt pool data, melt pool size data. We calibrate these observations at various points for calibrating and validating our model. And then we have another model for predicting the part scale grain distribution, which is called the discrete dendrite dynamics model. And from that, we can predict the grain distribution for the entire part. After that, we isolate particular set of grains and do a global local analysis for train it with machine learning algorithm for a particular grain shape to find out what is the, to predict what is the grain scale residual stress on the grain. Next slide, please. So some details about this model. So we have the thermal property requirements for which basically solves the 3D heat conduction equation along with the thermal boundary conditions. And this is the heat source is represented as a double ellipsoidal heat source, which is pretty much common in welding and wire arc additive manufacturing literature. So now for the double ellipsoid heat source as represented by this equation, we need to calibrate it by determining these parameters A, B, and C, which we'll show in the next slide. So we do a single track deposition, and from that we identify what from the cross section we identify we measure the width, and the half of the width is shown here, the width and the depth, and compare it with our finite element simulation to determine these values A, B, and C, so that we can calibrate this heat source for upcoming analysis for the residual stress and the other processes. So next slide, please. So then we have a lot mechanical for solving the mechanical equation, solving for the stresses. We require mechanical property requirements, which is the uniaxial stress strain, possibly at different temperatures, which is provided by Dr. Song's group. Then we calculate the thermal strain, which is responsible because of the differences in the coefficient of thermal expansion. This coefficient of thermal expansion is also provided by Professor Song's group. Then we solve for the constitutive equations depending based on the elastic properties of the material, temperature dependent elastic properties. Then develop then identify a yield criteria based on the different temperature based on temperature dependent yield stress. And then develop a yielding procedure, so based on isotropic hardening for solving the evolving stresses during the deposition process. Next slide. So this is a video representation of the simulation for a 50 mm cylinder. I think the video is stopped. So here I have simulated 15 layers. On one side I represent the temperature field, evolving temperature field in degree C, and on the other side the effective stress for 15 layers. So in total the cylinder is about 22 layers, I'm able to simulate the entire cylinder, whereas I'm only showing about 15 layers of the simulation here. The simulation took about 68 hours for completion. Next slide, please.
Now we need to wrap up. Our time is up.
So in the next slide, there is a comparison between the thermocouple data, where at different locations and the location of measurement locations are shown in this slide. So we have a pretty much good comparison coming up between the temperature cycles, particularly the cooling rates. And then next slide, please. This work is still ongoing for the calibration. And then I have present some results about our discrete and dynamics model for predicting the grain microstructure at for the entire part scale. So this is for one particular case about a multi-track deposition. So we take the melt pool dimensions that we calibrated in the previous slides and use it for predicting the grain texture evaluation at different parts. And compare the pole figures at different locations for calibrating this and validating this model. Next slide.
I think this the next slide is the final slide. Basically, I would like to say we're at the stage where we converge and move into the calibration of ICME model, finishing that, and then we will move forward with a high throughput experiments and using different printing strategies and see the difference of location specific. And hopefully we can see the location specific. Right now, we only see the difference of the different pattern. And we will start to do a little bit more with characterization supporting the machine learning. So that's the next stage. And I think we finished the presentation. Thank you very much. Any questions? Later on.
Correct. We'll hold all questions to the end of the session. And so thank you, Wei and Sen-Tan. Then our next presentation is on a project that's at Carnegie Mellon, and our presentation is Nan Gao. We could get his slides up, and he can begin whenever they're put. There we go. So please go ahead and start.
Okay, so can you zoom out the size right now? Okay, all right. So my name is Nan Gao, a PhD student from Carnegie Mellon University. So today I'm going to present my work on behalf of my advisor, Professor Elizabeth Hom. So because she has a teaching class during this time frame. So my research is about computer vision and machine learning, making the processing microstructure and the property connection in heat-resistant alloys. Next slide, please. So I think every material scientist is familiar with PSP connection. So PSP connection is a processing microstructure and property connections. This is a fundamental tenet of the material science, is that processing generates microstructures that mediates the material properties. So we can see the figure on the left side. So the property and the processing and microstructure are correlated and affect each other. Among these three aspects, the microstructure is the most important because it's the key link between what we can control, the processing the parameters, and what we can achieve, the material properties. So we want to study the connections between these three aspects. So next slide, please. So we believe machine learning techniques will be a good candidate to explore the PSP connections, given its ability to find the relations in large, complex data sets. So we think machine learning seems to tailor-made for exploring PSP connections. So in these projects, we develop and apply computer vision tools to create quantitative representations of the microstructure images and apply machine learning models to answer the following questions. So can we predict material properties from the images of the microstructures? So next slide, please. So this is the pipeline for our research. First, we will collect microstructure image data and the property map data for the heat-resistant alloy system. Second, we will develop computer vision techniques to extract knowledge from the microstructure images. Third, we will create a machine learning system to find the relations between the microstructures and the property metadata. Fourth, we will analyze and interpret the result to discover new PSP connections. Next, please. So we have two data sets for our research. The first one is the image data. The image data is SEM images for the nichrome alloy. And on the left side is a second data set, which is a property map data set. So we have the data samples and their corresponding mechanical property like the UTS and the yield strength. So in this research, we were using the yield strength for the predict the mechanical properties. So next slide, please. Maybe some of the material scientists are familiar with the computer visions and the CNNs, but right now I will give some brief introduction about what's the CV and the CNN. So actually the computer visions is a field of the artificial intelligence that enables computers and systems to derive meaningful information from the digital images, videos, and other visual inputs. So the most widely applications of the computer visions may be the autonomous cars, so like Teslas. So they have the capability to see the world somehow like the humans. So they can distinguish what they see, is this the humans or the cars? So the most computer vision algorithm use CNN, which we call the convolutional neural networks for the learning process. So a CNN is a model that used in the computer visions to extract features like the textures and edges from the spatial data. So on the left corners, so we can see the workflows of the CNNs. If we have the input images, when they fit into the feature learning modules, so the modules will consist of the convolutions and some pooling layers. So after feature learning modules, so we have a vector which can represent what we learn from the CNN, and then we will apply the features to the classification models. So after these steps, so the models can tell you what they see. So is this a car or truck or vans? So next slide, please. So in this specific research, we are using the VG16, which is a type of the CNN models in our research. So this is the figures shows what the VG6 doing in this research. So if we have the images, so we can throw this image into the VG16 models. So we can use the convolution layers to extract the features from the images. So we call this step feature representations. So for different images, they will have the different features. So we call this characteristic vectors. So after we pull out the characteristic vector from each images, so we will make a regression models to build connections between the vectors and their mechanical properties. So this is the most important step in our research. So next slide, please. Okay, so this is the first experiments we will try for our data. So the first one is that we will make a predictions of the yield strength on small sample series. So we have a bunch of data, but we don't want to make things too complicated at first. So for the first experiment, so we just choose 3 sample series. So the criterion for the selections is just based on the difference of their yield strength. So we can see from the right plot. So we can see that for different sample series, we have different yield strengths. For some of these, they have very similar yield strengths. So at first, if we want to predict the similar ones, so it will be too complete. So at this stage, so we just choose 3 sample series, which is the HR53, HR66, and the HR68. So this is the corresponding SEM images for the sample series. So next slide, please. So after applying the CNN models to the images, so we can get their features for each images. So after applying the visualization models, so which we use here is a PCA and T-SNEs. So we can see the data distributions for each images. So we can see that for these 3 data series, they tend to class into 3 groups. So actually, this is a good indicator for the visualization step. So we can see that the CNN models have a good representation vectors for the images. So next slide, please. After we have the vector for each images, so we want to make connections with their corresponding yield strength. So we build regression models for our datasets. So right now we have the prediction arrows for each data point. So in this research, the prediction arrow is actually the difference between the true values and the predicted values of the yield strength. So in this research, we also defined accurate predictions as a prediction with the 15 MPa, considering that experiment arrows of the measuring the yield strength. So for the prediction accuracy of these regression models, so the accuracy is about 87. Actually, we can keep optimizing these models and to gain the much better result. We didn't spend too much time because the ultimate goal is to predict the yield strength for all the data sets. So let's go to the next slide, please. So for the second experiment, we expand our datasets to 7 sample series. So we can see that we want to include more data into our prediction system. So the key issues will be that, can we predict the yield strength for the different classes with very close yield strengths just based on their visual difference? So for the this 7 sample series, so we can see these their corresponding SEM images. But for some series, like from the HR52 to HR58, so they have very similar yield strength. So our prediction models are able to recognize the difference between them. So that's a key issues. So next slide, please. Okay, so follow the same steps. So we are using the feature visualizations for the features after using the CNNs. So we can see that the issues are, if we can recognize the difference between the interclass, which is a data point has a large different yield strength, and the intraclass, which is a data point has a close yield strength. So the second issue is that if we can distinguish the similarity of the interclass. So from the data visualizations of these features, so we think we have the capability to do this, because for these 7 different sample series, we can see that there are 7 groups of the data distributions in the t-SNEs. And for some of the groups, they have the similar yield strengths. So I label with brown colors. So we can see that these 4 groups tend to stay close with each other in these grid sections. So that's a good point. So because from the data visualization views, our models have the capabilities to extract characteristic features from the images. So next slide, please. So after some optimizations and selections from the regression models, so we have the best prediction accuracy here is that after we're using the XG boostings for our datasets, we can get accuracy as high as the 96. So here is the prediction arrows corresponding to each data point and the distributions of the arrows. So right now we have the conclusions that after applying the VGG16 models and the XG boostings for our regression models, so we can have a good predictions for our data set. So next slide, please. Actually, during the experiments, we try different regression models, so we can see how the regression models involved with the accuracies. So we can see these compressions of the different regression models. So we can see that if the arrows has much narrow distributions, so we can have the improve the regression process. So right now, the best predictions for the predictions will be 96 based on the XG boosting. So next slide, please. So this is a summary for our research. So in order to answer questions, so can we predict the materials properties from the images of material microstructures? So first, so we built image data and property data to explore the PSP connections. So the second, data is selected and processed via CV and ML task. The third one is the VGG16 is used to extract features from the image dataset, and characteristic features are used to make connections between the properties. Fourth, the VGG16 shows a high interpretabilities for feature presentations method. And the five is the regression models are well built to predict the yield stress and of the heat resistant alloys. So the prediction accuracies can be as high as 96. So next. Okay, so thanks for all the audience. That's it.
And thank you, Don. So what we'll do now is we'll go into our last presentation in the cross-cutting research area. And this is another round 6 project. It's being done at Princeton University, and our speaker is Giuseppe D'Alessio. So
hello.
There we go.
Can you hear me?
Yes.
Okay. Good morning. My name is Giuseppe D'Alessio, and I am a postdoc from the Department of Mechanical and Aerospace Engineering from Princeton University. And today I will present a project called Adaptive Depth Neural Networks for Scale Bridging Modeling of Multiphase Reacting Flows. Next slide, please. Now, in the field of chemically reacting flows, the application of machine learning algorithms could really be groundbreaking because of the physical complexity of the problem we are dealing with. And in fact, we have to deal with a multi-physics problem because of the coupling between the fluid dynamics, the chemical kinetics, and heat transfer. We have to deal with a multi-scale problem because of the partial overlap between the chemical timescales and the fluid dynamics timescales. We also have to deal with a prohibitive dimensionality because of the large number of chemical species taken into account by the kinetic mechanisms, and with a large amount of data which are produced by high fidelity simulations such as direct numerical simulations. Next slide, please. Now, in particular, in light of the computational costs of the CFD simulations of these reacting systems, we are interested in the development of a general framework for a scale bridging modeling between high fidelity simulations and coarse grain simulations. And this means that we want to use the information which can be found in the data obtained from CFD simulations where complex fine scale structures are solved to model physical quantities in coarse grain simulations. And we want to focus on industrially relevant applications of multi-phase chemically reacting flows, such as fluidized beds. Of course, the computational investigation for this kind of applications cannot be accomplished by means of high fidelity simulations because of the high number of scales involved and the large number of species. And therefore, the only way to numerically investigate multi-phase reacting flows at an industrial scale is by means of filtered to fluid models, which require appropriate closure models. And thus, we are building an automated workflow for a database scale bridging modeling between high fidelity simulations and filtered to fluid models, TFM. Next slide, please. For now, we have started working on gas phase combustion data. And in particular, we are focusing on a direct numerical simulation of a premixed hydrogen flame. We have two different flames configuration varying the inlet diameter. Moreover, for each simulation, we have applied 4 different filter sizes. And so for each simulation, we have 4 training data. Next slide, please. Now, in combustion, one very important variable is the progress variable. It's important is mainly due to the fact that it is used to track the progress of the chemical reaction. And in particular, since we are operating with a hydrogen flame, the progress variable can be set equal to the mass fraction of water. Now, to perform coarse grain modeling, an unclosed quantity which is related to the progress variable is its associated filter dissipation. And this quantity can be modeled by means of the Pierce model, which is a physical model. Next slide, please. Nevertheless, it is also possible to model mathematically this quantity by means of an artificial neural networks. And as you can see from this slide, the results are very accurate by means of this mathematical modeling, thanks to the intrinsic nonlinearity of this kind of regression method. Next slide, please. Now, although the results for this particular regression are very satisfying, several questions are still open. In first place, what we want to know is if it is possible to increase the accuracy of the mathematical model and to accelerate the training time. Secondly, we want to know if we can automate the selection of the inputs without any prior knowledge of the physics. And finally, we want to know if it is possible to automatically select the best architecture and hyperparameters for the ANN. And moreover, what we would like to do is also to enforce a physical constraint within the mathematical model. Next slide, please. Now, the pipeline that we propose to address all these questions is the following one. So as you can see, it consists of three different steps. The first one is the data preprocessing, then the dimensionality reduction, and the third one is the numerical modeling. Next slide, please. Okay, now let's examine the first step. Next slide, please. Now, when working with high fidelity data, it is very frequent to work with an input matrix accounting for a large number of statistical observations because of the very high number of grid points that are required for the numerical simulation. And now, this could be an issue in terms of computational cost, memory requirements, and also tendency to overfit. And consequently, it may be good to reduce the size of the input matrix by means of a sampling strategy before the machine learning section. Now, one of the easiest and at the same time most effective strategies to sample the data is by conditioning the input matrix by means of any of its variables. Next slide, please. So basically what we do is to divide one of its variables in k different groups between its minimum and its maximum, and from each of these groups we select a fixed number of points randomly. Now, although we are in fact choosing the points randomly, this approach is way more effective than a global random sampling on the input matrix because of its local nature, and therefore the sample space will be also very dense and uniform. Next slide, please. Now, as a proof, we can see that in our case, we can go from a matrix accounting for 4 million of statistical observations to a 750,000 statistical observation matrix. And now in this slide, we are actually comparing the sampled space with the original space of the full input matrix. Now, since of course the input space is high dimensional, we can plot only one variable at the time, and we are comparing the red dotted space, which is the sampled one, with the black squares, which is the one spun by the full input matrix. And we can actually say that the sampling strategy is effective because all the black squares are fully covered by the red dots, and therefore there aren't zones of the high dimensional space which are not taken into account by the sampled matrix. Next slide, please. Okay, now let's go to the second step of the pipeline. Next slide, please. Now, in real world problems, we usually work with multivariate data, and so we have to deal with variables which have different units and ranges, and therefore when we apply any kind of machine learning algorithm, we have to normalize the data so that the columns of the input matrix are coherent. And so usually this operation is accomplished by means of a statistical quantity such as the standard deviation. Next slide, please. Now, from the Buckingham pi theorem, though, we know that considering k fundamental dimensions, we can find p minus k dimensionless groups. Or in alternative, we can find p minus k plus 1 dimensionally consistent groups. And now, in addition, by doing this, we get standardized data, and at the same time, we reduce the number of input variables. Next slide, please. I think there is a lag.
Yeah,
Okay,
we've been
thanks.
okay.
Now, for this particular problem, we have 4 fundamental dimensions, and therefore we can go from a 8-dimensional input to a 5-dimensionally consistent input. Next slide, please. Now, by doing that, the result is that we get a smaller network, and at the same time, we have a lower testing error and a lower train time. Now, if P is large and K is small, though, we could have that P minus K plus 1 is still large, and therefore we could have to further reduce the dimensionality of our space. Next slide, please. Now, one of the most employed dimensionality reduction techniques is the principal component analysis, PCA, which basically consists of a spectral decomposition of the covariance matrix associated to the input matrix. Now, after the decomposition, we get 2 different matrices, a matrix A of the eigenvectors or principal components, and a matrix L of the eigenvalues, which represent the portion of information accounted by each principal component. Next slide, please. Now, for this particular framework, the application of the PCA algorithm seems very appropriate because it is possible to automatically determine the optimal dimensionality of the reduced manifold by inspecting the cumulative sum of the eigenvalues and the total sum of the eigenvalues. So in this case, from the analysis of the eigenvalues distribution, we have that a 5-dimensional manifold is enough to explain almost 100% of the original input data variance. And also, this is the same dimensionality that we have obtained from the computation of the pi groups. Next slide, please. So now the last step of the pipeline is the numerical modeling. Next slide, please. One important thing that has to be taken into account when working with ANNs is that there are no defined rules to set their architectures a priori, just analyzing the input data. And thus, what we are doing right now is to apply an iterative algorithm which has a mathematical objective function, which is defined by the minimization of the minimum absolute error to select the best architecture for our ANN in an unsupervised fashion. Next slide, please. So what we want to do in the short to the medium period is first finding a way to enforce physical constraints into the mathematical model to increase the regression accuracy. And in fact, we have that many physical variables are strictly positive or non-negative by definition. And now, if we predict in the original input space, output space, we have that, depending of course on the ANN accuracy, the variable of interest can be positive, 0, or negative. Whereas if we predict in the log space, we have that our variable of interest must be strictly positive. Next slide, please. Now, the second thing that we want to do is also to integrate the on-the-fly learning curves diagnostics to avoid overfitting. And in fact, we have that it is very easy to recognize an overfitting behavior. And it is possible to do that just by looking at the curves for the train and for the test set. And so by means of a technique which is called early stopping, we can interrupt the training of the ANN before the network starts overfitting. Next slide, please. Now, another thing that we want to do, of course, is to extend the framework to multi-phase chemically reacting flows. And in fact, as I mentioned at the beginning of the presentation, our main objective is to train a framework on massive TFM numerical simulations to then automatically get a reduced model to be used for the corresponding filtered TFM. And in addition, what we want to do is also to perform data analysis on high fidelity simulations of multi-phase chemically reacting flows by means of model order reduction techniques to optimally select the best input variables in an unsupervised fashion, and also to really understand the correlation between the inputs and the outputs of our problem. Next slide, please. Now, with regard to the project schedule, what we are doing in this first year is the identification of target applications and closure models. And also, we are doing the a priori testing of the proposed pipeline, as well as of the algorithms in the steps of the proposed pipeline. And then during the second year, what we plan to do instead is the a posteriori validation of the framework on the target application that we selected during the first year. And after that, we will implement the optimized framework into the NodeWorks software. And finally, we will use the software for database scale-bridging modeling between high fidelity simulations and filtered TFM. And in particular, these last two tasks will be accomplished by means of a very close collaboration with the ETL researchers. So next slide, please. So thank you for your attention.
Okay, appreciate it. So that concludes our cross-cutting research portion of today's agenda. The next item on the agenda is the Q&A. Now, during these presentations, I had not seen any questions come in through either the question box or the chat. Actually, I do see a question coming in right now. Okay, great. So Giuseppe, this question is for you. This is from Sham. The fact that the PI group and the principal component analysis gave 5 as the optimal dimension is only by chance. What are your thoughts on that? And we can unmute Sham in case there's anything he wants to clarify.
I don't know if it is by chance, but because I think that it might be that let's say the underlying dimensionality of our data is really 5-dimensional. So it's it is that it might be that probably the algorithms are let's say both discovering let's say the real dimensionality of our data, and the thing is that what we plan to do eventually is also to see if we can further reduce the dimensionality applying the pi groups, so finding the pi groups and then applying the PCA algorithm on the let's say the input matrix which has already been reduced by means of the pi group. So coupling a let's say physics-based dimensionality reduction with the pi groups with the mathematical let's say dimensionality reduction such as PCA.
Okay, and if we have Sham unmuted, are there any follow-up comments?
No, thank you. I think, what I understand is you are using pi group analysis to make an initial reduction in the dimensionality, which makes sense, and then use principal component analysis to further reduce, right? The pi group analysis does not lose any information because it completely covers the entire solution or the parameter space, but the principal component analysis then helps you to reduce the dimension by choosing to say take 99% of the energy or something like that. So that, okay, thank you.
Okay, great. Thanks, Champ. I'm not currently seeing any other questions, so it is 12:15, and we do have the option of starting our lunch 10 minutes early in the interest of, giving everyone some more of their time back. I think we'll go ahead and do that. So I guess that concludes our morning portion. Our afternoon portion will include presentations from Hanjing Tian, Andres Starakovsky, and Muhammad Salim. If you three are on, could you stay on real quick for a mic check? Everyone else, you I guess are dismissed for lunch, and we will reconvene at 12:55 p.m. Thank you. Muhammad, I think you had already done a mic check, so I think. Okay, it is 12:54. Bruce, can you hear me? Is my audio coming out okay?
Yep, you're fine.
All right, perfect. Why don't we go ahead and get Hanjing's slides up?
Yeah, this is Hanji.
Yep, I can hear you loud and clear.
Okay.
We're gonna get your slides up. It's the only presentation under advanced coal processing, so then we'll do the Q&A right after.
Thank you for introduction. This is Hanjing, and I'm actually initial with WVU when writing the proposal, but recently moved to the University of Kentucky Center for the Applied Energy Research. And I think yesterday, the UCFER manager mentioned that there's one project didn't start yet. That actually this is this project. Very sorry, the project actually is heavily delayed because of my transfer. Sorry for everybody. So the title of the project is Economically Viable Technology for Production of Co-Derived Aerogel Insulation Envelope. In this talk, I will use it as a kickoff meeting presentation, and I will present some background and our primary result and some of the progress that I would like to share with the NETL and all the user forum members. Next slide, please. Oh, I cannot. Okay, the overall objective is to develop this co-derived aerogel, and this material we use as an isolation envelope. Aerogel is a very important material for the insulation, and our goal is to achieve the thermal resistance R value between the 14 to 105. The talk will give about the background, objective, then I will talk about approach and a little bit about project details because the project has not formally started up yet. Next slide, please. So why we do this advanced co-processing, as I mentioned, introduced, this is the only presentation that in this area
And because the DOE believe that the advice in the co-derived building materials is mainly for the carbon form, roofing, siding, and isolation could provide some benefits, including the lower price and the superior property to the existing building material. And I will show you how this material will apply in the building in next few slides. And another goal is we can create a new value chain for the industrial, which generally do not use the coal as their process. And certainly when we actually found the new market and the new value for the coal, we can decrease the usage of the coal for the combustion. Therefore, we can decrease the greenhouse gas of the CO2 emission. That's all target of the program and my goal to this project too. Next slide, please. So talk a little bit about the aerogel, these materials. I show you the two fingers. The left finger actually show what is the research of the aerogel in the evolution. I mean, aerogel actually is not new concept. It's invented about a century ago. And the first aerogel is the silicon oxide aerogel. Right now it's fully commercialized. And in the 1990s, for the first time, we prepared the carbon-based aerogel. But because the carbon-based aerogel, we do have some disadvantage, and we actually add some polymer inside, so we call it polymer reinforced carbon aerogels. And you can see actually silicon aerogel has a long-term history, but the carbon aerogel is fairly new in last 2 decades, and still research hot topic right now. And in the right side, I give you the number of paper published over the year, and you can see after year of 2000, the publication in this area, the skyrocket. It's very hot topic right now. So compared to the single component that basically is carbon aerogel, if we can add some plastic and metal oxide to reinforce the aerogels, we can get very good physical and chemical properties, better flame retardance, physical strength, and thermal conductivities, so that we could have the better, the wider application in the industrials. So basically, from the report, the plastic-based aerogel will have R value 0.024. Depend on the preparation method, the BT area goes to higher of about 200 meter square gram. Generally, aerogel itself can be very stable at the high temperatures. Their melting point is above 2000 degrees Celsius. But if we add the plastic inside, suddenly the temperature will decrease, melting point will decrease, but still generate above 500 degrees Celsius. That is suitable for the building materials. Next slide, please. So aerogel research actually is not only, as I mentioned here, it has a wide federal report. NETL is working on that. And for long term, the ERE the Building Technology Office has supported this area too. I actually also I didn't present here, but I know the NASA actually has also long-term support for the aerogel research. This slide show you is from the EREBT technical report, and they claim the less than 1 inch aerogel-based isolation pretty much equivalent to the 3 inch of the fiberglass. So that's why they are working on very strong on these areas. The right finger actually show you the picture actually provided by my industrial partners, and they can build the aerogel. This actually is a carbon-based aerogel. They can build this aerogel in roll or in the envelope, but certainly this project I will provide the envelope shape. And at the bottom picture is actually a picture the industrial of my friend actually take in the Scotland, and they use this aerogel to repair some adequate buildings. And you can see there's on-site construction here. Next slide, please. So, general approach for the aerogel form include the 4 steps. The step 1 is the sol-gel method, which is pretty similar to the catalysis sol-gel process. And after that, we need long-term aging. So the organic template as well as carbon, they will bond it together to make the perfect network structures. Then after that goes to step 3 about the drying. So generally it's supercritical CO2 drying, and we make the aerogel structures. So finally is carbonized. So carbonized is to build the single component carbon aerogels. But the step 4 actually is not necessary for this current program, because we do need the physical strength, and it's okay for us to leave the plastic template or the polymer template in the aerogel structures. So that will cut a lot of cost for the overall preparation. The key actually for the overall approach, I believe this is not only for my project, it's critical for the all project that processing the coal, is how to depolymerization the coal structures. I mentioned to you, this is a Nature Communication publication, I think it's from Rice University. And in order to decompromise the coal, they actually use concentration chloride acid and nitric acid solvent. So the overall temperature 120 degrees C, 24 hours, and a full step to deploymize the coal. The coal certainly is a very, very stable structures if you want to process the coal. And I will show you what is our technical approach to do this step. Next slide, please. So the objective again is this is our technical goal. We want to demonstrate the polymerization of the depolymerization of the coal into the carbon nanoparticles under the mine temperature. So compare with that Nature Communication publication, where we are going to achieve it less than 150 degrees C, less than 2 hours, and less than 0.3 megapascals. So we will validate the production of the PVC or the clay-based reinforced carbon aerogel production, and we do expect the yield will achieve 30% and 1 kilogram per day productivity, and the BET area goes to 300 meter square per gram. So finally, if we want to derive this envelope as a product, we will working with WV together to characterize their thermal and mechanical properties. Next slide, please. So this is the overall summary of the patent technical approach. It's patented by myself and Georgia Institute of Technology. And we already patented both US and also the world patent. I show you the number here. So different from the conventional chloride acid or nitric acid, we will use the what we call the continuous one-pot technology to decompose the coal. And the major solvent will go to DMF. That is organic solvent. It's very popular in the organic chemistry. And we will add the chloride-based, basically chloride iron or some other chloride as the catalyst. We go through the low pressure hydrothermal reactors to decompromise the coal. Then after centrifugal filters, we will add the clay and the polymers to process the polymerization reactor again, so that the aerogel will be reinforced and cross-linked with the polymer compounds. So finally it goes to drying. Drying process, we achieve the aerogel product. One mentioned that DMF as a solvent will be recycled. So this organic, we will minimize organic solvent usage so that the overall process will not impact the environment. Next slide, please. Show you the demonstration of the carbon nanoparticles. Actually, the carbon nanoparticles from this patent is a common quantum dots product, which is generally in the 30 to 60 nanometer particle size. And as I mentioned here, we are not go through the strong acid polymerization, and we use the DMF and the iron chloride as a catalyst. So overall, we will release the CO and in the in the reactor, but it's actually slowly increase the pressure. So initially, we do not. It's not necessary to put the reactor in pretty much high pressure. They will slowly increase up. So the right picture I show you is the product that we produced. That is the carbon quantum dots, and you can see the fluorescence, very strong fluorescence that is demonstrates the success preparation in the nanoparticles. And I want to mention that this particle actually is in it's multi-colors, multi-fluorescence, and at least this sample that I collect is we have the 3 different fluorescence band, and you can also see what's different from the visible light and the UV excitation, which demonstrates the success preparation of the nanoparticles. Next slide, please. So we are going to polymerize these carbon materials, carbon nanoparticles with the clay, for example, bentonite or magnetite. That actually has the interlayers structure and the intralayers structures. And we are also polymerize the carbon nanoparticles with the monomer or polymer structures so that we will build reinforced gel composition. So that is what we are going to do. And the right side, I already show you. This is the product that's prepared in my lab. And this is the aerogel that's reinforced by the, actually it's reinforced not by the PVC actually. That's a little bit difficult, but this one is prepared by the polyetherenes. I believe the follow the same procedure. We can use different different plastic to reinforce the carbon materials so that to achieve the program goals. Next slide, please. So after we get the carbon aerogels, and we are going to prepare and produce the different shape of the building envelopes. This technology, step 3 technology, actually is open shelf technology, and in our lab we already developed we have a long time history to develop such of carbon-based materials. The left one actually is the carbon building envelope. Actually, you can see the carbon is reinforced in the middle, and the plastic is actually in the edge, two sides. The middle one is carbon form. We actually prepared this is old technology we prepared by the supercritical water. And the right side picture is the carbon fibers that developed in my lab. Next slide. So overall project schedule, as I mentioned, the project it's not started yet, but we are going to spend 2 years working on the process optimization of the patterned carbon nanoparticle sensors, and we will prepare the co-derived aerogel and to process the drying technologies. And finally, we will produce the aerogel into the plastic envelopes, and so that we can achieve the mass production. And suddenly we will test their thermomechanical characterization and brief cost analysis for the whole project. I hope in the close collaboration with my industry partner and with the NETL collaborator, as well as 2 WVU scientists, we will finish the project as early as possible to catch up the program a little bit. Next slide, please. So collaboration work with NETL, basically, as I mentioned, it's not started yet, but this is what we need from the NETL. We want the multi-wavelength Raman, because this is this is carbon-based materials. So Raman will play a critical role to characterize the carbon crystalline structures. And because this is a mixture of the carbon with the different material, and in most process, the carbon actually is in the liquid phase. So we do need the UV-based Raman to avoid the fluorescence. That is a main goal that we are working with NETL. and because I actually, this is original from the proposal, actually it's not necessary now. Because I'm in the University of Kentucky, we already have very, very good STM in the center. So we can do most of the microscope work here, but certainly I can share the data with Intel. And I also want to communicate with Intel on the technology economic communication. We do have industrial partners that actually development. They're very interested in this project, and we wish when we talk about the industrial partner, the Intel could involve with our discussions so that we can have the good perspective in the future program. Next slide, please. So at the last slides, I would thank Penn State team, especially Bruce Miller, and the NETL, my project manager Alma, to support, to continue support this project even under my transition from WU to the UK. And certainly I would thank my boss in the UK here, Dr. Kunlei Liu, and give me a lot of support to continue this project. Thank you very much. That's all my talk.
Okay, thank you, Hanjing. We do have a couple questions. Number one, are there other barriers facing the potential commercialization of coal-derived aerogels, such as passing applicable standards and codes, like for NFPA fire protection and safety, insurance considerations, or aesthetic considerations, the black color or how the product looks, which should influence customer acceptance? Part of this question is cut off, so can we, oh no, okay. Influence customer acceptance was the last part. So let's unmute Mark Freeman, and Hanjing, we are running a little short on time, so if you could keep your answer brief.
We actually talk with the project manager, the industrial partners, and I show this data and to our industrial partner. I mean, so far they actually very interested, and also they actually told me this product, if fully developed, will be used as the outside materials, outside of the building. So they do care some property, but they do not care too much. The only thing they actually request to me is as I mentioned before, is R value, and that is a major issue they concern. Another one is moisture. So they think the BET area is so high, and they actually to see how many moistures they can absorb for a long term. But they agree this is the moisture problem is generally a wide big issue for the aerogels. This company is specifically working on the aerogels, and they are confident that if this goes to product, they have the capacity to solve the moisture issue by their own technology. Okay. Yeah.
Okay, so the last question I'll just reframe as a comment, because we did catch that the project duration, the proposed duration, is longer than the remaining time on the UCFER contract as a whole. So we'll have to speak offline on perhaps adjusting the scope as necessary, because there will not be enough time for a 24-month project. So we'll talk offline. But thank you for your presentation. That was all the questions that we had for advanced coal processing. So once again, appreciated. And if we can get the next presentation queued up, Bruce, I'll let you do the introduction.
Okay, sure. Yes, next we're going to have two presentations in the fuel cell technologies area. The first one's going to be by Andrei Starakovsky from Princeton. And go ahead and start, Andrei, as soon as you're ready.
Thank you very much for introduction. Good afternoon, everybody. I would like to discuss development of novel supersonic hybrid non-equilibrium plasma reactor for production of solid carbon. And it's just a joint effort between Princeton University and Sandia National Laboratories. Next slide, please. Yep. Basically, the idea is very simple and very well known. So if we have a lot of methane, if we put it into the plasma, we can dissociate methane. Partially, we will have production of hydrogen, H2 molecules. We will have production, of course, of heavy hydrocarbons, C2, C3, C5, and all others. And we will have production of black carbon. The trick is, of course, efficient production of these materials, because we have very different types of plasma. Below, I just put a brief summary of some types of discharges, just to make an impression of what types of plasma we have in our hands. On the right side, we have discharges at very high electrical fields. When we have a very strong acceleration of electrons and electron temperature reaches tens of eV, and in this case, of course, we have rather cold gas, very hot electrons, and almost all the influence of our plasma on gas is direct dissociation and ionization of our molecules by electron impact. So in this case, we have very efficient, of course, ionization. We have efficient dissociation. The problem is each dissociation, each separation of hydrogen atom from methane molecule will cost us approximately 20 eV. So energy cost is rather high. On the other side of this graph, we have arc discharges. Arc discharge with almost equilibrium plasma is degree of non-equilibrium is not very high. In this case, of course, we still have acceleration of electrons in the electrical field. We have all this energy transfer from electrons to molecules, to translational degrees of freedom of molecules. But temperature of electrons and temperature of heavy particles are not that different that much. We have approximately several thousand K in our discharge channel. But it is too hot to produce something valuable. Temperature is too high, and typically we are using arc discharges for welding or for something like that, when we really need very high temperature. Somewhere in between, we have discharges at a moderate temperature of heavy particles, about 4,000 K, so-called. Microwave discharges are in this group, and gliding arcs. So transient discharges with transient plasma. It is what we would like to use in our conditions. Next slide, please. Generally, the idea is to create some rather hot gas using some volumetrical discharge. Typical temperature in the discharge channel should be around 3,000 or 4,000 K. And as you can see in the graph, in these conditions, we will have almost complete dissociation of our methane to carbon and hydrogen. But after that, the tricky part is to create black carbon and molecular hydrogen instead of forming methane during the cooling process. So if we will have very slow cooling, we will, of course, generate all these heavy hydrocarbons. We will generate methane back. We will not generate solid carbon. We will not generate molecular hydrogen. We need very fast cooling to prevent reverse reactions. That's why we propose to use supersonic nozzle. In supersonic nozzle, we have very fast gas expansion. We decrease temperature. We decrease gas density. So we stop all chemical reactions. We typically freeze our chemical composition. So we can produce something in relatively hot discharge. After that, in supersonic nozzle, we immediately stop all chemical reactions. So we have our products in chemically non-equilibrium regime. Next slide, please. What we are trying to do right now, transversal discharge in supersonic flow. In critical section of our nozzle, gas pressure reaches approximately half atmosphere. Initial pressure is about 1 atmosphere of 100% methane. In critical section, we have flow velocity about half kilometer per second, so rather fast flow. And we would like to stabilize the discharge across this sonic flow, transonic flow. And after that, very fast expansion will give us desired products. To decrease the time of cooling down, decrease of time of expansion time, we use a rather small nozzle. Critical diameter is 1.3 millimeter, and typical cooling time is only 8 microseconds. In 8 microseconds, we reach Mach number 3. We decrease the pressure 2 orders of magnitude. We decrease density more to approximately 20 times. We decrease temperature about 4 times. So we are cooling down our flow rather quickly, and we freeze all the products. And next slide, please. It just image how it looks like in reality. So what we have, left picture demonstrates the nozzle, critical cross-section of the nozzle without plasma. Central picture shows vacuum discharge before flow starts. So we have already high voltage applied to high voltage electrodes, but right now we have no methane. So we have basically vacuum arc. And right picture demonstrates real conditions. Flow is in design regime. The gas density is approximately 60% of normal density in the critical section of the nozzle, and at the exit of the nozzle we have Mach 3 gas flow. So of course we cannot block the flow completely through the nozzle. Discharge occupies approximately just some part of the nozzle and hits only part of the gas. And after that, the gas expands in the supersonic part of the nozzle. Next slide. Plasma parameters typically depend on voltage, of course, depend on density of current, depend on channel. So we use nanosecond periodic discharge. Typical frequency of discharge pulses was 120 kilohertz. So between pulses we have approximately 8 to 9 microseconds. Typical voltage is approximately 2 kilovolts, and mean power of the discharge was only 3.5 watts. So it's a rather low energy discharge, which just designed for to minimize the energy we need to convert our methane to some valuable products. Next slide, please. Some discharges, some details about the discharge pulse. As I mentioned, typical voltage at the start of the pulse was about 2 kilovolts, and after that it drops down almost immediately because we have rather high current, approximately 1 ampere between our electrodes. It was the typical pulse current. Discharge produces peak power about 150 watts and average power was about 3 watts. And as you can see, we can maintain a plasma channel. We can maintain current through our discharge system, through our electrodes for about 1 microsecond. During 1 microsecond, with gas velocity about half kilometer per second, we have displacement of the discharge channel for about 0.5 millimeters. So displacement 0.5 millimeters and distance between electrodes 1.3 millimeters. Discharge channel, of course, is bended in our flow, but not we have this bending is not critical. We still can maintain conductivity in our channel during this 1 microsecond, and we have some energy deposition. And typical energy deposition per pulse is about 5 microjoules. Next slide, please. We tried to, of course, to model as a discharge development in methane in all details. We have very nice set of self-consistent cross sections for excitation and scattering of electrons on methane molecules. We have a couple of two processes at 0.16 eV and 0.36 eV. It's vibrational excitation of different vibrational modes of methane. We have excitation at 9 eV, 10, 11, 12 eV, which correspond to excitation of different electronical degrees of freedom. And this process could lead to dissociation of methane. But as I mentioned, the energy price of direct dissociation by electron impact is too high. So we are going to use some thermal dissociation, which give us much lower energy cost of dissociation. And we have two ionization channels at 12.6 and 14.3 eV, which produce electrons and generate our plasma. So typical hydrodynamic approximation, we have of course different processes which we have to take into account. Ionization, attachment, recombination, and photoionization. Photoionization is very important because positive discharge, for example, cannot propagate without photoionization in the discharge gap. All electrons from our gas will immediately came to electrode and discharge will stop. So we need some production of additional electrons in front of our ionization wave. Next slide, please. But in methane, the mechanism of photoionization is strongly suppressed by huge cross sections in vacuum ultraviolet range of spectra for methane, just for dissociation of methane. So we have a lot of dissociation by ultraviolet photons, and we have much less photoionization, because all these photons will be spent for dissociation. That's why we have almost no positive wave. And as you can see, for 5 nanoseconds, we have development of negative wave from left to right. And we have no propagation of positive wave from right to left from positive electrode. And this wave appears only when this negative wave reaches positive electrode. So we have step-by-step formation of our discharge. First of all, we have propagation of negative wave from our cathode to anode. After that, this avalanche reaches anode, and we start just typical streamer because we already have some ionization in our discharge gap. And in the middle, you can see propagation of this positive discharge from right to left and formation of steady state channel between electrodes. Just right picture demonstrates this steady state configuration of electrical field and electron density. And as you can see, we have very thin channel close to a discharge axis, which formed between the electrodes. Next slide. Just to demonstrate what is going on along the axis of our discharge. It's a one-dimensional picture right now. We have a propagation of, on the right side, right lower picture demonstrates propagation of our ionization wave in terms of electron density. So ionization wave propagates from left to right, reaches anode, and after that we have propagation of reverse wave, redistribution of potential, and dramatic increase of the electron density. So we have this propagation back and forth in different directions. Next slide, please. As a result, we are forming along the axis very thin and very conductive channel of the gas, like pulse spark. And in this pulse spark, we have significant energy release. This pulse current, about 1 ampere for hundreds of nanoseconds, could overheat our gas up to 4000 K. And picture on right side shows what will happen with our gas during this 1 microsecond if we will just have a significant energy release. We have almost complete dissociation of our methane. We have production of hydrogen molecules. We have a little bit of atomic hydrogen, but it is still not very high because of very fast recombination. Our pressure is 0.5 atmosphere. After that, we have expansion of this dissociated flow in our supersonic nozzle. So basically, we would like to freeze this composition because we have already a lot of molecular hydrogen. We have almost no methane in our thin channel across supersonic flow. And predictions give us estimation that typical energy price for molecular hydrogen will be approximately typical flow of molecular hydrogen will be approximately 4 to 10 to 18 molecules per second in our conditions. Next slide, please. So what we have from the measurements in our vacuum chamber, we can sample the probe and we can do some chromatographic analysis. In subsonic regime, when nozzle is in off-design regime and flow acceleration and flow cooling is not very fast, we have energy for hydrogen production approximately 3.2 electron volts per molecule, and overall hydrogen energy of production cost will be about 40 kilowatt hours per kilogram of hydrogen. And energy for methane dissociation is 1.6 electron volt per molecule in these conditions. In supersonic regime, when we have very fast expansion, and it is what we are looking for from the point of view of efficiency, very fast cooling, freezing of chemical composition of our gas, we have typical energy for hydrogen production about 28 kilowatt hour per kilogram of hydrogen, and energy for methane dissociation is only 1 electron volt per molecule. So it is what we, basically what we are looking for, very high energy, very high efficiency of production of molecular hydrogen and relatively low cost for dissociation of methane molecules. Just below, there are a couple of examples of production of hydrogen in electrolysis process require approximately 3 times more energy, and hydrogen combustion give us approximately 140 megajoules per kilogram of the energy, so much more than we have to spend for production of hydrogen in these conditions. Next slide, please. So as a conclusion, we built this novel supersonic reactor with non-equilibrium plasma, and we can freeze the composition of our plasma products in fast supersonic flow, and we can reach relatively high efficiency of hydrogen production in such conditions. And theoretical estimations give us even better energy cost for hydrogen production, so we have some room for improvement for the future. Next slide. And as future plans, from the point of view of experiment, of course, we would like to make our discharge more stable. We need not just periodic regime, we need more or less DC regime of our discharge to increase the production of hydrogen in our nozzle. And we need more details about the products. For example, we would like to analyze heavy hydrocarbons production and black carbon composition we are producing in our nozzle. From the point of view of modeling, we would like to model complete flow in the nozzle, expanding flow with all the details and dynamics of nanoparticles formation. And of course, from the point of view of diagnostics, we need more details about our plasma. Thank you for your attention.
And thank you for that presentation. We have one more presentation under the fuel cell technologies, and that will be given by Muhammad Salim from Penn State. So if we can get his slides up, there we go.
Yes, thank you. Right, so thank you for the introduction. My name is Muhammad Salim. I'm a postdoctoral scholar working for Professor Vanderwall at the Penn State University EMS Energy Institute. The experimental work for this project was started this past April when I joined my position. I think delays were from COVID, which I think everyone experienced. So this work is entitled The Metal-Free Catalyzed Synthesis of Novel Carbon by Carbon Allotrope Seeds. So next slide, please. So this work was funded through round 4 of the UCFER consortium. This work's relevance to the research area R2 is the focus of hydrogen generation. And in this case, thermocatalytic decomposition, so TCD, with the added benefits of novel solid carbon formation. A quick overview. So our goal, or what I'll be showing, is that we can overcome catalyst deactivation and address catalyst regeneration in traditional TCD catalysts, and we can negate the need for separation and recovery of the catalyzed carbon from catalyst in TCD. Essentially, necessitated by the high decomposition temperature for natural gas decomposition, traditional metal catalysts deactivate because of carbon growth at active sites on the metal catalyst particle, and essentially the full encapsulation of these metal catalyst particles. Our objective here is to bypass these problems. Right, you want to bypass these problems through the use of carbon catalysts. Right, so I'm going to show that we have established a proof of concept for carbon allotrope segments as new catalyst systems for TCD, and we can optimize the amount or the type of high value carbon produced through this methodology. Next slide, please. So a brief outline of what I'll be covering. I'm going to go through some quick background on thermocatalytic decomposition, or TCD, the current status of TCD with metal catalysts, and some advantages in relation to how these metal catalysts operate, some advantages of carbon catalysts in this regime. Some experimental approaches and research objectives. So I'll go through some applications and techniques that we have used, and our current results and summary of our results, and the planned research targets and future work. Right, so this work was really started in April. I think we've gotten some great results since then, and the targets of this work are we mentioned at the end. So next slide, please. Okay, so quick background on TCD. So it's a attractive alternative to conventional steam reforming. And this is for the reason that it does not generate CO or CO2 or carbon monoxide, carbon dioxide byproducts, and nor does it consume water resources as compared to conventional steam reforming processes. Stock desulfurization and steam generation are really eliminated because we're not going through those methods. And the attractive, one of the attractive advantages of TCD is that the energy requirement for cracking methane is less than that for steam reforming. Right? So if the whole entire process really requires less energy input for hydrogen production. And yeah, next slide, please. Okay. So the current status of TCD of methane in metal-supported catalyst. So I mentioned in the previous slide that the activation energy for cracking of methane, so from going from methane to hydrogen production with nanocarbon formation. So if you look at the picture on the left side, it's this. In this case, it's a nickel or a metal base catalyst. The activation energy is reduced through the use of this catalyst, right? So less energy input. During this process, hydrogen is produced, nanocarbons formation. If we look at the middle figure, right, so the supported metal catalyst in this sense serves to decompose methane in a stepwise fashion. Right, so the methane is interacting, it's catalyzed by the metal particle. Carbon is essentially depositing onto the particle, and hydrogen is emitted. Right, so this results in hydrogen production and carbon deposition, where this process can form useful nanoproducts, right? One example of this nanoproduct is carbon nanotubes. And I guess as is well known for nanotubes, and not just nanotubes, but other metal catalyzed nanocarbon forms, these catalysts become coked, right? They become encapsulated, they become deactivated. Essentially, they are embedded and encapsulated in the nanotube or the nanoform, right? So you can sort of see that in the bottom figure. I have some more high resolution figures on the next slide, but before we switch over, the 2 points to take from this are that traditional metal catalysts are deactivated during TCD, and they are also embedded within the carbon product. In this case, they are difficult to remove. So next slide, please. Okay, so the SEM and TEM of CNT, so this is using a metal catalyst particle, right? So the darker area, so if you look at the middle top figure, right? So this is a CNT prepared using, in this case, a tungsten metal catalyst. You can see the encapsulation of the metal particle. You can also see that it's completely embedded within the CNT, right? So I'm just using CNT as an example, but other nanoforms, we can also see this issue where the metal catalyst is embedded within the produced carbon nanoform, right? And this metal catalyst, depending on the application of this carbon nanoform, it can have various detrimental effects on how this carbon formation can be used. So typically, these metals are wanted to be removed from the carbon nanoform, and that requires chemical or physical processes which end up damaging usually the usefulness of, or being detrimental to the usefulness of our nanoformations. So next slide, please. So this is one advantage of using a carbon catalyst. Some other advantages are that these carbon catalysts are insensitive to sulfur poisoning. The deposited carbon has multiple commercial uses, and this sort of goes back to my previous point that metal catalysts need to be removed for being detrimental really to some of these uses, especially as electrode material. The use of a carbon catalyst would essentially eliminate the need for the removal of the catalyst from the produced carbon nanoforms. And then ideally, it has the potential to be self-regenerating or auto-catalytic. And I included a picture here. So on the TEM image, we can see the semi-ordered concentric lamella as in a normal carbon black. Next slide, please. Okay. Okay. So addressing TCD and regeneration research needs. So ideally, if we want to grow a specific carbon form, the best place to start would be to start with a specific carbon form, right? So whatever we grow is going to be determined partially by the form of carbon that we start with, right? So we want to find this relation between nanostructure. By this I mean the lamella of the carbon catalyst particle that we're using and our TCD rates, right? So as we're performing this TCD, what is the relation between these two items? And then the purpose or the onus behind this is that as carbon deposits, the original catalyst is buried. So if you look at this image on the bottom right, so the darker lines, if we imagine that as the lamella of the nascent carbon, as we're depositing, as this is acting as a catalyst during TCD, we're depositing carbon nanoformations on the surface of this nascent carbon. And we can imagine that as the lighter layers above that. So as it's depositing, each subsequent layer of TCD is catalyzed by the preceding deposited carbon, right? So each layer by layer, every layer that's formed is catalyzed by the previous layer. So ideally, this can be autocatalytic through each layer having active sites capable of further catalyzed TCD reactions. If this nanostructure, again, of the nascent carbon could be controlled by a combination of TCD and or initial catalyst, self-catalyzed or autocatalytic behavior could be imagined. Next slide, please. Okay, so a quick overview of our experimental approach and slide before I get into some figures. So we're going to be using carbon black as catalyst. So the reason behind this is one, it's integral to the product and it's, I guess most importantly, compatible with the product structure, right? If we're forming a certain lamella, the carbon black can be compatible with the structure. It's not going to have some detrimental effects that metals will have, that as I mentioned earlier. Experimentally, the morphology is easily to distinguish from novel carbon formation, right? Carbon black has a very distinct structure, right? It has this concentric lamella, and it's homogeneous with each particle. And since it's a powder, it can be supported or used as an aerosol, right? We can deposit this as the thin film for reactions, or we can deposit just as a powder itself, or we can use that as an aerosol. Since it's a powder, we can aerosolize this and perform TCD in its aerosol form. And then lastly, we can evaluate morphologically distinct nanostructure forms. Again, this is referring to the lamella of the nanostructure forms of the carbon black catalyst particles. All right, we're talking about the rates and forms of carbon formations, and we want to connect them with the base nanostructure of the carbon black catalyst. Next slide, please. Okay, so a quick research progress. So we are applying different techniques and carbon catalysts for TCD with different permutations of fuel, inert air ratios with different carbon catalysts. Essentially, we pursue two different types of experiment systems through a design of experiment approach, where the temperature, the fuel, and or the ratios have been independent variables or factors with various carbon catalyst seeds. And so in this case, I'm showing two examples. So one would be the use of a furnace for TCD, or the use of a seeded carbon catalyst source through an aerosol into a flame synthesis, into a catalyst seeded flame. So a fixed bed reactor and a aerosolized carbon seeded flame. So the furnaces that we have some very high temperature furnaces that can go up to 1650 C, but we were using different fuels for TCD, different ratios, different catalysts, and I have some pictures on the next slide. So next slide, please. So the experimental design was using our sophisticated custom gas flow controller setup. This was to regulate pre and post flow gas mixing for furnace and seeded flame synthesis. So on the picture on the left, there's a electronically controlled fuels and inerts and oxidizers input into fuel controllers for partial pressure or molar fraction control for pre or post gas mixing into furnaces. So on the right, high temperature furnaces, which were able to do different types of seeded or hotbed reactions under. Next slide, please. Okay. Oh, okay. So I'm going to show one example of, in detail, one example of what we're able to accomplish in the step-by-step manner. So it's clear what sort of carbon formations are being produced. So this is one type of carbon black which we tried under specific reaction conditions, which you'll see in a moment. So this single type of carbon black, this was nascent. So this was not treated. This was just nascent carbon black. The next slide is going to show the treatment of this at 1500 C under inert. So next slide, please. Okay. So this is treatment of carbon black, our catalyst under inert atmosphere. Comparing this to the previous slide, just some things that are important to note is that the particle size has not changed. The surface has not changed, right? This looks, essentially nothing has changed, right? The particle is quite distinct, the exact same as nascent carbon black, right? So these two TEMs look ideally the exact same between before treatment under inert and after treatment under inert. Again, what we're looking for, before I go to the next slide, what we're looking for is not the form of the structure, but the nanostructure specifically, right? If what we could be forming is irregular or chaotic, right? So like the lamella, the nanostructure. So next slide, please. Okay, so this is under reaction under methane for this specific carbon black at 1500 C. And we can see a clear, distinct difference in the low resolution and the high resolution structure. So we're seeing this chaotic, disrupted nanostructure or irregular growth. Next slide, please. So if you compare, I'll go to the high resolution again in a moment, but if you compare the low resolution of the treatment under argon with the low resolution treatment under our methane conditions and our fixed bed reactor conditions, we can see a clear, distinct change, right? Rather than the semi-ordered concentric lamella as a normal ordered carbon black, we're seeing this chaotic growth of these nanocarbon forms, clear and distinct between the two. Right? We could imagine that on the left side, this nanostructure is contained within the structure on the right, and the nanocarbon forms have grown from our carbon black catalyst. Next slide, please. Sorry, next slide, please.
Looks like we're just dealing with another delay.
Okay, thank you. So this is the comparison of the high resolution TEM between the two. Again, on the left side, the treatment under inert, we don't see any change between nascent and inert. We see the same concentric traditional carbon black images. On the right, we see the formed chaotic structure. Right? The significance of this deposited carbon is that this chaotic structure, that the nanostructure that we're seeing here, this form will have more active sites than the nascent carbon black catalyst, right? And in this sense, these active sites will allow for more growth or more propagation of active sites than the initial carbon and essentially be autocatalytic. And we can see this when we start comparing, we start altering the reaction parameters, times, concentrations, etc. Right, so the ideal, if I can refer back to the keyword, is that this is sort of autocatalytic. Okay, so next slide, please. So just another TEM comparison of the same treatment areas, just showing that we see this difference really everywhere. And next slide. Okay, so the summary of these results is that we have shown TCD using carbon catalysts to be a promising process, which I think is pretty apparent in what we've shown here, but that carbon black as a seed catalyst can be self-propagating and rate maintaining. The next really step for us and what we've sort of tried to show thus far is that the optimization of these chaotic nanostructure formation is possible through the control of carbon seed catalyst and reaction conditions, right? By controlling our initial carbon seed catalyst or by controlling our reaction conditions, we could ideally get different forms or different amounts of chaotic carbon formations. And next slide. So if you want to grow a specific form, the place to start is always to use a specific form.
Sorry, it doesn't want to refresh for some reason.
That's all right. Okay. So our next steps, our next target for this research is primarily to investigate the active site generation and propagation. We have if you look at the top right, we have an Altamir AMI 300 chemisorption analyzer in tandem with the gas chromatograph. So we can use this to investigate the active sites, but also to measure the kinetic rates. It's a microreactor, and the GC allows us for characterization of this. In the bottom right is a graphitization furnace. So we can use this to anneal material and change the active sites as reference comparisons, right? So this goes up to 3000 C. Through changing active sites at this temperature, we can use this as a reference comparison to other formed nanocarbons. And next slide, and last slide. And thank you. My contact information is at the bottom left, and Professor van der Waals' information as well.
All right, perfect. Thank you, Mohammed. So it looks like that concludes our session on fuel cell technologies. We'll be going into a brief Q&A before our break at 2:10. I see two questions that came. I believe they were in response to the first presentation. So if Andre is still on, I see that he is. Great. So the first question is, will this technique work on biomass particles?
On biomass particles, yes, sure, why not? The only problem, we will have some oxygen in our system. So we'll have production of a little bit more byproducts. But still, we can dissociate, of course, everything.
Okay, great. And Lauren or Justin, if you could unmute Richard Bajura, that would be great, just in case there are any follow-up comments to these answers. He asked another question, Andre. Can the process be scaled up to a commercial size?
Yes, definitely. We are, of course, thinking about how to scale up everything. We have definitely a lot of problems because the size of our plasma channel means the rate of cooling down. So the smaller the size, faster cooling down, or more efficient process. So we need to keep the size of our plasma and size of the nozzle as small as possible. But nobody will prevent us from using some array of nozzles. So right now, what we are looking for is something like multi-hole nozzle, which generate supersonic flow in a very big area. But every single nozzle should be rather small. So we have some prospects to scale up.
Okay, great. And Richard, we've unmuted you in case you have any follow-up questions or comments. Do you have any for Andre?
What happens with the carbon that's generated?
Right now, we are just collecting everything using paper bags.
Thank you.
And Richard, you asked another question. I'm not quite sure if it was a follow-on to the ones you asked Andre or one in response to Mohammed.
It's in response to Mohammed, and I couldn't think and type at the same time. As I heard him say, you start with a certain form that you want and you continue to get that form. My question is centered around the applications of the forms that you get, needles and cross linkages and stuff like that, that give the different carbon products different characteristics. Can you maintain the characteristics of the same form and control what that form would be, so that you might get an application that would be used for tennis rackets versus one that would be used for aerogels or something like that?
Oh, I was muted. Right. So ideally, I guess to highlight, I'll direct this to your question, but to highlight the goal of this is that we wanted to get an autocatalytic system. So the form that we make, we want to have either be more active or as active as the form that we start with. To design a particular form product is the goal, right? We want to start with the form and have under either the starting form or controlling the reaction conditions. Yes, we want to be able to get a target form that we could use for different applications. As you saw in our results that we were able to achieve that I showed here, the form that we produced was a chaotic nanocarbon form, right? You can see the chaotic lamella nanostructure, and it's able to TC is able to further promote this because that chaotic form has active sites that then can be propagated through other chaotic forms.
Okay.
Thank you. I don't know that I'm clear in my own mind what my question is, but thank you for the additional input.
All
Yes,
right, appreciate it, Richard. Okay, so it doesn't look like we had any additional questions come in, even though we have a couple of minutes left before our break. So if additional questions do come in, feel free to either type them into the chat box or the question box, depending on whether you are a panelist or attendee, and we will try to get those answered throughout the day. So in the meantime, I think we can go ahead and start our afternoon break, if we can get that slide up. So after our break, which will end at 2:20, we will begin our session on gasification systems and coal biomass to liquids. If James and Michael are on, we will ask you to stay on very briefly for a quick mic check, as well as Albert Presto and Justin Richter. If either of you guys are on as well, let's get them unmuted just to see if their audio is working. For the rest of you, we will reconvene at 2:20. Thank you.
Hi, this is James. Can you all hear me?
Great. Thank you, James. Yep, loud and clear.
Great, thank you.
All right, Michael, University of Utah, do we have him on? Yes, I see him.
I'm here.
Okay, perfect. Thank you. Albert, his presentation isn't until later, but if he's on, we might as well give it a shot. Albert Presto. Okay, I'm not seeing him. Do we have
him or Justin?
Okay. All right, we'll wait for those two. It's not until later anyway. Okay, let's reconvene at 2:20.
Okay, it is 2:20, so why don't we go ahead and get started. James, if you're on, Bruce, I'll let you do the introductions, and then we can start the application.
Okay. Yeah, okay. So we all have two presentations here in the areas of gasification systems and CCBTL. And the first presentation is by James McCone from the University of Pittsburgh. Go ahead, James.
Great, thank you so much. And thanks everybody who's on the line for joining today, and for Department of Energy and the organizers for the opportunity to discuss some of the work that we're doing at the University of Pittsburgh. Again, I'm James McCone. I'm leading one of the UCFER projects over at Pitt in collaboration with Guts Fazer and Yanni Born-Pakis in the chemical engineering program. We're also working on a sort of consulting basis with Doug Kaufman's group at the National Energy Technology Lab. Go ahead and next slide for me, please. Right, so this is my sort of pre-canned overview of my research group. We run an electrochemical engineering group that does a pretty equal mixture of fundamental and applied research in the area. And actually some of the things that I have to share today, we'll touch on both of those more fundamental and applied research programs. And specifically the area that I will be discussing today relates to our program on thermoelectrochemical catalysis. And even more specifically, our UCFER funded project is oriented toward methanol synthesis from syngas-derived, coal-derived syngas, where the objective is to use electrochemical activation, or maybe what we like to call electrochemical intensification, to enable that process to occur at considerably lower temperatures than would be normal for the current industrial practice. Next slide, please. I assume it's more lag than, that's fine.
Yes. Yep, working on it.
It's my own fault for having large photos, I think.
Who knows? How's it going, Justin?
I'm going to try to stop sharing my screen and then restart that.
Okay.
I can go ahead and talk over the top on the next part anyway, and when the slide shows, then it will. There it is. Right. So like a broader premise of the work that we're really interested in is to consider the fact that just, you know, in consideration of the desire to reduce the carbon intensity of all of our chemical manufacturing, you still need to get a lot of carbon from somewhere. And you see that illustrated in the left-hand side of this slide, that out of the top 5 produced commodity chemicals, 4 out of the 5, ethylene, methanol, propylene, and BTX, of course, are all very carbon intense. And so there's no reason in principle that we can't continue to rely on resources like coal in the near term, or maybe even in the long term, as the basis of carbon in our chemical economy, even as we try to decarbonize. And so a huge proportion of the work in my lab is thinking about how do we say valorize coal or CO2 emissions, or whatever it is that we want to use as the basis of carbon, by coming up with clever ways to activate hydrogen toward hydrogenation reactions and the like. Next slide again, please. Another sort of conceptual motivation, of course, is that being able to use electrochemistry for this will really benefit from the fact that renewables are becoming so inexpensive, and one can anticipate that the supply, and perhaps even oversupply at certain times of the day or certain times of the year, of renewable electrons will allow us to start to build out some of this electrochemically intensified chemical manufacturing technology at remarkably low cost. So again, this is just an illustration of some of the predictions and realizations of how quickly costs for, in this case, solar have come down over the years. Next slide again, please. And so again, for context, our research group thinks about the hydrogen component of this to take oxidized hydrocarbons, whether it's carbon monoxide, carbon dioxide elements, either in syngas or in captured emissions, and how to generate or regenerate useful fuels and chemicals from those materials. And so we sort of hedge our bets by focusing heavily, you can go ahead and click forward, on water electrolysis technology to just generate H2 that could be fit into a value chain in which you're relying pretty heavily on thermocatalytic reactivity and simply need to get hydrogen from somewhere, and why not do it with an electrolyzer? We also study more complex integrated systems, which is the basis of our UCFER project, where we imagine integrating multiple process steps that would be normally employed if you had ready access to hydrogen all into one unit in an intensified electrochemical thermocatalytic reactor. Next. Right, so here's an example of an embodiment of the types of chemical reactors that we have envisioned and that we're working on. And again, I want to emphasize that this is just an exemplary case, and I'll try to emphasize what the key component here is, which is we call them electrochemically pumped membrane reactors. And again, this is sort of a classification scheme that we're trying to come up with, wherein we are linking thermochemical steps and electrochemical steps across a charged conducting membrane. And simply because I had a very pretty diagram put together for one particular embodiment that involves CO2 as the precursor, that's what's shown here. But again, one can envision taking any relatively low value or readily available feedstocks that involve oxidized carbon precursors, again, syngas, carbon dioxide, even gasified biomass, or waste plastics that have been oxidatively gasified or what have you, could all be used as the basis of this process. And we're, of course, as many chemists and chemical engineers, inspired by the machinery of biological systems and photosynthesis in particular, and thinking about the fact that individual reactive steps in these processes are carried out in physically distinct locations. And so the ability to transport charge over relatively long distances, nanometers to microns, maybe even tens of microns, can be really advantageous for enabling unique reactivity, because the physical chemical environments that can be quite different across long distances. Next slide, please. Right, so more specifically, the type of chemical reactor that we're interested in here relies in part, or again, one embodiment that we're really excited about, it involves using ceramic metal oxide materials as the basis of these hydrogen or ion conducting systems. And so this is not too dissimilar from what you'd see, say, in a solid oxide fuel cell or in proton conducting ceramics, except that the types of materials that we're intending to rely on here are in fact mixed conductors. And if there's time in the Q&A, maybe at the end of my talk, I can discuss a bit more about the specifics about why we're interested in mixed conductors and how that causes these reactors to look different from the types of electrolyzer or fuel cell architectures that you often see in this type of chemical manufacturing scheme. But in any case, we at the outset of the project, and in fact a little bit before we started the UCFER project, we had sort of a wish list of what we needed from the types of charge conductors that we were hoping to be able to use in these reactors, and they're listed here. I won't maybe read them all out, but that ultimately led us to a class of materials called transition metal hydrogen bronze compounds, so of the formula H sub X, MO sub Y. Transition metals like titanium, vanadium, molybdenum, tungsten oxides, all are known to absorb a B with a B, as in into their internal structure, hydrogen ions with concomitant electron transfer. And this type of chemistry is exactly the same type of cation intercalation that you would see in lithium-ion batteries, only it's with hydrogen. And now you can imagine moving that hydrogen over macroscopic distances and reacting it in a completely different location than when it was absorbed into the oxide. Next slide, please. Right, so the first piece that I'm going to talk about today is, again, some more fundamental work that my lab has done in collaboration with Gutzwasser and with Yanni Brompakis to actually first our work with Professor Brompakis on thinking about some of the characteristics on this wish list and trying to prove out that, in fact, this class of materials can do the type of chemistry that we want. Next slide, please. So the key feature here is to think about having congruent reactivity under thermochemical conditions and electrochemical conditions. And so again, focusing on the ability of these metal oxides to absorb hydrogen into their bulk structure, it turns out that that type of reactivity had been observed for many, many years within the scope of ongoing research in thermochemical catalysis, where it's called hydrogen spillover, and in electrochemistry, where it would be called hydrogen intercalation. And so I have just two schemes that are very prevalent in the research literature about how these things work. Spillover being usually using dihydrogen as a reactant, that is where the HH bond is split by a catalytic unit like platinum, and then the hydrogen is thought to physically migrate over onto a metal oxide support and can ultimately be absorbed into that structure to create a new chemical compound, the hydrogen bronze compound. Cation intercalation is a little bit different because you think about the charges coming from different locations, the electron being injected from an electrode, and then the hydrogen atom coming from a proton source in an electrolyte. So again, the classical pictures imply that there are actually different pathways here, one involving neutral hydrogen transfer across the surface and then into the bulk versus the movement of charged species, one coming from one place and the other coming from an electrode. Next slide, please. So my graduate student, Evan Mew, very talented student, now entering his 4th year at Pitt, designed what I think to be a very clever experiment in which we were able to physically observe the rate of this reaction and actually the subsequent migration of hydrogen over millimeter distances by inducing that hydrogen uptake process under thermocatalytic and electrocatalytic conditions, otherwise under identical experimental conditions, where we are observing, it turns out, over the top of a metal oxide film that's going to undergo this type of hydrogen uptake, the progress of the reaction. And so there's an animation in the upper right that may or may not be showing up properly for you all, but the idea is that it looks a little bit like the eclipse of the moon, right? That you're observing what turns out to be a very distinct color change in this material that proceeds with hydrogen uptake. And so we can observe that over time. Please slide forward for me, please. We can observe that over time and translate that change in optical properties into what we call a spillover front, which is to say the leading front of hydrogen uptake in the material, and then translate that into a time course. And then when we do this under, again, electrochemical and thermochemical conditions, if you can actually go to the next slide yet again, we see some interesting results, which is that if we induce this reaction to occur under electrochemical conditions, we observe a particular rate at which that chemical reaction and linked hydrogen transport process occur. And it turns out that that rate of initial hydrogen migration is way, way too fast to be gated by the diffusion of either protons or hydrogen atoms. And in fact, that process is much more likely to be reaction rate limited, which is to say it's just however fast you can induce a chemical reduction to happen within the, in this case, tungsten oxide crystal lattice. And in fact, if we also cause that reaction to happen under thermochemical conditions, meaning we expose to, it turns out, dissolved H2, but we carefully control those conditions so that they're directly analogous to the free energy of reaction that we can induce under electrochemical conditions, we see exactly the same dynamics. And so what that leads us to conclude, I think, slide forward for me, please. Yeah, what that leads us to conclude is that in fact this chemistry is probably happening under essentially the same conditions and mechanism, regardless of whether we induce it to occur electrochemically or thermocatalytically. And in fact, that reaction is also probably happening in a way that's best described as what I would call the quote-unquote electrochemical hydrogen intercalation mechanism, even when you're exposing the substrate to H2 gas. And so more specifically, the schematic on the left is showing that even, again, in the presence of H2 gas, what's really happening is that hydrogen is coming into electrochemical equilibrium with a platinum electrode, in this case, or a platinum catalyst, and that's inducing electron transfer into the tungsten oxide. But when the environment contains a significant fraction of protons, which is true in our experiment because we're bathing the whole system in a protic electrolyte, then the protons can come from a completely different place. And so this is sort of a long way of saying that, again, that charge transfer and a process that is best described as hydrogen intercalation is probably occurring regardless of whether the reaction is being driven with H2 gas or with an applied potential in the presence of protons. Next slide, please. So that congruent reactivity is helpful and useful to us in the context of trying to link together electrochemical and thermochemical steps in a full reactor. The next thing that I'll talk just very briefly about is our use of computational tools to try to learn more about the thermodynamics and other kinetic and transport limitations that might exist in these systems, with the ultimate goal of being able to predict the reactivity and therefore tune the reactivity to match whatever the reactant of interest is. For example, relatively carbon rich or maybe carbon monoxide or carbon dioxide rich syngas that would be coming out of coal. So next slide, please. So again, I'll just talk very briefly about this. This is the work that now is much more closely directed by Professor Bormpakis, Yanni Bormpakis, and actually the same graduate student, Evan Mew, who's been splitting his time between experimental and computational work for the last several years, where we used a combination of quantum chemical simulations and some statistical and I would call them very simple machine learning type algorithms, more like elaborate equation fits, really, to use very simple describable properties of the parent oxides, meaning pure tungsten trioxide as the parent material for a hydrogen tungsten bronze, and simply based on the acid-base properties and the chemical configuration, which is to say where the atoms are in the parent material, we can do a pretty good job, if you could click forward for me, of predicting right, again, based on acid-base properties, which are all calculable in the parent material, and then we use a series of correlations to try to extract what the resulting hydrogen intercalation and therefore hydrogen uptake properties will be. Click forward one more time for me, please. We can make pretty solid predictions in these calculations of what the thermodynamics of hydrogen uptake in these materials will actually be. So let me just restate, because I think that wasn't maybe the clearest explanation. What we can actually do is, based only on the structural information of the parent oxide, with these models pretty quickly predict what the electrochemical and thermodynamics of hydrogen uptake in these materials will be, which is pretty powerful when we imagine that now we can draw on a large library of relatively simple and even relatively complex metal oxide compounds and start to think about tuning composition and structure for the desired reactivity, and then translating between the thermodynamic conditions that we would observe in an electrochemical system and in a thermocatalytic system. Next slide, please. Oh, yeah, so there's an example of that on the right here, where we've now basically taken a set of 4 different metal oxides and considered the range of electrochemical potentials and therefore the thermodynamics of hydrogen, reactive hydrogen that is contained within these metal oxide structures, which can be essentially translated directly to the equivalent reactivity of gas phase hydrogen or the free energy of hydrogenation of any number of substrates. And so this leads us to conclude, for example, that tungsten-based oxides are actually not very good candidates for activating hydrogen in a way that would allow us to convert, say, CO2 into methanol. But titanium-based oxides ought to be better because they're sufficiently reducing once you've put hydrogen into them. Next slide. So as a sort of unexpected opportunity that emerged from this type of analogous studies of thermocatalytic and electrocatalytic reactivity, we came to appreciate that it ought to be possible now to, again, use very straightforward electrochemical measurements and calculations to predict the reactivity of hydrogen with these oxides to start to engage the possibility of a chemical looping type systems, which are purely thermocatalytic, wherein we're now doing chemical looping hydrogenation reactions instead of the more traditional chemical looping, say, oxidation reactions for carbon capture, for example. And so we showed, again, just this proof of concept up to this point in the project, that we can actually, using a model reaction of acetylene hydrogenation, predict, sorry, click forward on my slide, please. We predict based purely on calculations and on experimental measurements carried out at room temperature in the span of a few minutes in electrochemistry that tungsten oxide ought to be able to engage in this acetylene hydrogenation reaction, whereas vanadium-based oxides ought not to be able to engage in that reactivity. Click forward one more time. And then indeed in experiment, this is exactly what we observed, that tungsten oxide, when charged with hydrogen under the appropriate thermocatalytic conditions, can do acetylene hydrogenation, and in fact even does selective acetylene partial hydrogenation to ethylene and doesn't produce a significant amount of ethane, whereas vanadium oxide is a spectator. It just sits there and stares at you. You can't really do any of this hydrogenation chemistry. So again, this is sort of an unexpected offshoot of the work that we've been doing throughout the UCFER effort in our lab to this point, to think about analogies between thermochemical and electrochemical reactivity. Okay, next slide. Just, I think, 2 more, and then I'll be done. Oh yeah, this is this sort of interesting process. We indeed show that the chemical looping process works. We can engage this types of catalytic reactivity through multiple cycles of switching back and forth between a hydrogen pulse, or I should say hydrogen exposure, and acetylene exposure to indeed confirm it's a catalytic process. We do see some deactivation over time, and we're still speculating about what the source of that is. And we actually, in fact, expect that it's that the lattice oxygen in tungsten oxide may in fact be somewhat reactive toward the acetylene precursor at these temperatures, which is in the 200 to 300 degree range, I think. Right, so there's more work to be done there, of course, but it's quite an interesting opportunity. Next, please. Right, so this brings us all the way back to the very beginning and thinking about membrane reactor schemes in which we're integrating electrochemical and thermochemical reactivity. And in fact, this scheme is different from the one that I showed earlier using metal oxides in a particular way, but it's much more congruent with our ultimate objective in making methanol from coal-derived syngas. And so you see this sort of scheme here where we're envisioning what really amounts to a concentration cell or a fuel cell setup in which we're intentionally trying to pump hydrogen from one side to the other and therefore manipulate its thermodynamic reactivity at any given temperature, so as to be able to integrate together electrochemical and thermocatalytic activation for some net benefit. And so there's just a schematic here of, again, of the reactor that we've designed. It's, as of just a couple of weeks ago, fully fabricated and up and running. And in fact, we're carrying out measurements literally as we speak on the first generation version of this membrane reactor. Next slide, please. Yeah, and I just wanted to show that this is, again, literally the very first example. Some of this work was inevitably delayed by lack of lab access due to COVID, but what you see here is a very clear evidence that, in fact, we're able to equilibrate thermodynamically the electrochemical potential across one of these membranes that we've designed, wherein we see the expected voltage signal in our electrochemistry measurement. Next slide. And I see that I'm out of time, and so I will just leave you with one final thought, which is what we're broadly interested in, and what I think would be worth considering more broadly in the research community, is whether or not there exist circumstances under which heat and electricity together can enhance catalytic reactivity more than either can individually. And then I'll just conclude with that last slide with a quick acknowledgement of members of my research group, of course, our collaborators and folks at the University of Pittsburgh and the Department of Energy for research support through this program. Thanks again very much.
Thank you, James. Very nice presentation. We will now go to our last presentation in this session, and this will be by, excuse me, Michael Negro from the University of Utah. If we can get his slides up. Uh-oh. That didn't look good.
Let me check in because Justin, are you there?
Hi, I'm still here. I'm trying to get the screen back.
Okay, no worries.
There we go.
Great. Thank you very much for the introduction. Next slide, please. So I would first like to introduce our team here at the University of Utah. Myself as the PI, and my co-PIs, Professors Bobby Mohanty, Eric Eddings, and Kevin Whitty. We've had 2 PhD students working on this project and a postdoc who worked part-time on the project at the very beginning when we started in August of last year. I would also like to mention our NETL collaborators, Debalina Dasgupta and Daniel Haynes. Next slide, please.
I'm sorry, it doesn't seem to be advancing. There we go. I think we're on the outline slide.
Okay, great. To give a brief overview of today's talk, I'll discuss the motivation for this work, then some of the materials synthesis, and then the reactor testing, and at the very end, the modeling results. Next slide, please. So the main goal of this project is to synthesize, characterize, and test new Fischer-Tropsch catalysts that have a higher heat conductivity and higher selectivity for long chain hydrocarbon products that could be used in fuels. Next slide, please. So Fischer-Tropsch synthesis is a means to convert synthesis gas, which we know is a mixture of CO and hydrogen, to hydrocarbons, and these hydrocarbons are usually fuels. And there are many ways to produce synthesis gas, coal, and biomass, just to name 2 means. Supported catalysts are often used for Fischer-Tropsch synthesis, and the active metals are usually cobalt, iron, or ruthenium nanoparticles. Fischer-Tropsch synthesis operates at elevated temperatures of between 200 and 350 degrees C, and at moderate pressures between 10 and 60 bars. A key element in Fischer-Tropsch synthesis is that it's a highly exothermic reaction with an enthalpy of reaction at minus 165 kilojoules per mole. This exothermicity leads to hotspots in the catalyst bed, and there needs to be a way to remove heat from these active sites and more evenly disperse it throughout the catalyst. So it's important to note also that the product distribution and the catalyst deactivation rate are both highly sensitive to temperature, and hot spots can then significantly change the selectivity and also accelerate deactivation processes. Next slide, please. So there is a critical need to remove heat from these hotspots, and our solution is to design a support with better heat transfer properties so that the hotspots can be minimized and deactivation can be slowed down. So we'll use a structured TiO2 nanotube support for our catalyst. We're also looking at carbon-based supports also, and control the acidity also of the catalyst to adjust the selectivity additionally. Next slide, please. So the expected outcomes of this work are new Fischer-Tropsch catalysts, which have better thermal conductivity, activity, and selectivity. This will provide for another responsible use of fossil resources that could potentially have a positive economic impact. Next slide, please. So we'll transition now from the motivation slides to the materials design and synthesis part of our work on the next several slides. Next slide, please. So our goal here is to synthesize new conductive bifunctional catalytic materials. We'll use 3D printing to make the support structures, and the support will either be titanium-based or graphite-based. And we started our work here with the titanium-based support material, with chosen iron cobalt bimetallic nanoparticles to be the active sites. Iron cobalt was chosen since it performs better than monometallic iron in hydrogen lean feedstocks where the syngas is derived from coal or biomass. The support will also be functionalized with acidic groups such as sulfuric acid groups that can be useful in both hydrocarbon growth and also hydrocracking and isomerization processes simultaneously. Again, in this project, we started work with the titanium-based materials and have made decent progress with those, and are beginning work with the carbon-based support materials. Next slide, please. So our goal in this project is to synthesize new 3D structured bifunctional catalysts for Fischer-Tropsch synthesis. Because we are using 3D printing, we can have more flexibility in the design of the structure of the catalyst, provided that, of course, the 3D printer is able to perform that printing. And so we plan to improve the heat transfer by using a structured catalyst, and using a structured catalyst will improve the heat transfer by increasing the number of contact points versus what would be normally observed in a randomly packed bed. So in a randomly packed bed, the heat transfer is usually enabled by gas phase convective heat transfer, and it's obvious that using a conductive support material should also improve heat transfer performance. Next slide, please. So our process for synthesizing the titanium-based materials is shown on this slide. The first step is to draw the structure in a CAD program, and then to perform CFD simulations to make sure that that structure is reasonable in terms of fluid flow heat transfer. And then there's a two-step anodization process to grow the TiO2 nanotubes from the titanium on the catalyst surface. After that is followed by an annealing step, and then after that we'll do the acid treatment using different concentrations of acids to get different acid site densities, and then after that we will impregnate the support with the iron and the cobalt, and then do calcination to finish the synthesis of the catalyst. Next slide, please. So the design that we formulated is shown on this slide in the lower right-hand corner. So this structure is designed to enable heat transfer away from the active sites that are dispersed throughout the structure, and move that heat radially away from the center. Next slide, please. So we did some test printing with polylactic acid polymer. As you can see, the design of the structure was reproduced quite well, and this gave us some promise that we could print the design with titanium metal. Next slide, please. So here is an example of a titanium 3D printed material before annealing on the left-hand side and after annealing on the right-hand side. We ran into quite a few problems with printing the titanium, as 3D printing with metals is less mature than 3D printing with polymers, but we were able to work through those difficulties. One of the main difficulties was with nozzle clogging, but we've been able to optimize the process such that we can avoid clogging of the nozzle as much as possible. Next slide, please. So we had an unexpected surprise whenever we were annealing the titanium 3D printed structure in argon. We observed the formation of titanium nitride. We still haven't been able to tell where the nitrogen is coming from, and in some samples it's even present in almost stoichiometric amounts. And if we look at the XRD on the bottom of the slide, there are some distinct titanium nitride peaks. The temperature program that we followed was as the manufacturer of the titanium filament had suggested. They actually had suggested annealing in air, but whenever we were observing nitrogen, we switched over to argon to see if it was possibly coming from the air. And the interesting thing is that titanium nitride has some potentially beneficial heat transfer properties that may assist in this project. Next slide, please. So we'll move on to the reactor testing part of this project. So next slide, please. So this is the reactor that we've built for this project. It did take much longer than I expected to build due to shipping delays and material shortages due to COVID. We have our gases flowing from the cylinders into the mass flow controllers, and then we have inside of the reactor a multi-point axial profile thermocouple. We also made two different diameter reactors, one to assess the kinetics, and a larger diameter reactor to better assess the heat transfer. And after the reactor, the products are analyzed with GCMS. Next slide, please. So we've prepared some unstructured powder catalysts for baseline testing. So we prepared iron on carbon, iron cobalt on carbon, iron on TiO2, and iron cobalt on TiO2. So they were synthesized and completely characterized using XRD, BET, and the usual characterization methods. Next slide, please. So these are the transient temperature profiles that we measured using the iron cobalt catalysts that are supported on TiO2. 0 represents the axial distance from the inlet, which is at the top of the reactor vertically. And as you move down the reactor, the temperature decreases due to convection, moving the heat from the bottom of the reactor to the top of the reactor. The same data is shown on the right panel, though in this case, the x-axis is now the axial length, and the colors of the curves correspond to the time on stream. Next slide, please. So this slide shows some of the results of the performance of the catalyst over 8 hours. The conversion remains relatively steady as a function of time. And the panel on the right shows the product distribution at the time point of 8 hours. Paraffins are shown here in black, and olefins are shown in red, and the total is shown in blue. As you can see, we have a relatively flat distribution of paraffins, and the distribution of olefins is mostly, most of them are found at lower carbon numbers. Next slide, please. So we have a reactor system that is working well, and so we've begun to test the structured titanium materials, and hopefully we'll have some exciting data to report soon. And the last bit of data that I want to share with you today is some of the results of the modeling. Next slide, please. And so we based our modeling work on this paper from the journal Catalysis Today. Next slide, please. And so the left panel on this slide shows the calculations as well as the experimental results from this paper. The blue in this case represents paraffins, and the red represents olefins. And the y-axis on both of these plots is the product formation rate. And on the right panel are our calculations, which give very similar results as the paper. Next slide, please. So this slide here shows the total hydrocarbon formation rate. On the left are the calculations and the experimental data from the paper that I had mentioned before, and on the right are the calculations of our work based on the model. Next slide, please. So this slide shows the 1 olefin to paraffin ratio. Again, the calculations and the experimental results from the paper are shown on the left, and our calculations, which match pretty closely, are shown on the right-hand side. Next slide, please. And so this slide here shows the results of some of our COMSOL modeling for the temperature profiles with TiO2 on the left and Ti on the right. As you move out from the center along the x-axis here, the temperatures converge to a specific boundary layer condition, and the TiO2 exhibits a slightly steeper temperature gradient, as it's not as good of a conductor as titanium. Next slide, please. And so for future work, we will add the iron cobalt nanoparticles to acid functionalized TiO2 structures that we have 3D printed. We'll also test the nanoparticles on the titanium nitride support. We'll also continue the reaction testing of the titanium 3D printed materials. We'll work on the 3D printing of the carbon-based structures, and we'll do some additional kinetic and CFD modeling. Next slide, please. And so I would like to thank the Department of Energy, NETL, and Penn State for funding this work. And I have more details of the other exciting work in my own research group on our website shown here. Thank you for your time and attention.
Great, thank you, Michael. And a thank you to James McCone for your presentation as well. This concludes the gasification systems portion of our agenda this afternoon. We'll be moving into the Q&A. I haven't seen any questions pop up. So what we're going to do is we're going to let everyone take a 10-minute break until we can resume with our natural gas technologies presentation. In the meantime, if you do have any questions, please either submit them through the chat box or directly through the questions box. Michael and James, if you guys can stay on momentarily while we wait for those questions to come in, if there are any, that would be great. And while the rest of you guys take a break until 3:10, we're going to do a mic check with Albert Presto. So thank you all. We'll reconvene at 3:10. And if you have any questions, please submit them. And Albert, if you're on, let's quickly test your audio. Okay, I'm seeing he's under panelist.
Okay. Can you hear me?
Yes, it's a little quiet, but I think your audio quality is still sufficient.
Okay. Here, I can grab, well, hopefully I can find some headphones here. Is that any better?
That's great, thank you. Okay, so just in the interest of letting people come in who anticipate the presentation starting on time, we'll take a break until 3:10. Thank you. All right, hopefully everyone's had enough time to get up and stretch. We will continue with our natural gas technologies presentation this afternoon. Presenting is Albert Presto of Carnegie Mellon University, and he'll talk about quantification of methane emissions from the natural gas gathering system using distributed sensors. Albert, you are unmuted, so you have the floor.
All right, thank you. So as I was introduced, I'm from Carnegie Mellon University. And so you can go to the next slide, please. So this project has two main objectives. The first is to show that we can use distributed low-cost sensors to quantify methane emissions, especially temporally varying methane emissions from the natural gas gathering infrastructure. And the second objective is to then actually apply this approach to measure emissions from gathering pipelines and pig launchers. And so the next slide, please. And so, of course, methane is the main component of natural gas, and it's also a greenhouse gas. So there's interest in understanding how much is emitted to the atmosphere. And emissions can occur basically at any stage of the natural gas life cycle. And here are just a bunch of photos, but the idea is, emissions can occur during drilling, during regular operation, from leaks at the well pad, or from, process related to emissions. They can happen at the end of a well's life, when the well is, if it's improperly sort of sealed at the end of its life. And those emissions can happen from leaking fittings, or from tanks, or etc. So there are a lot of places where these can occur. And if you hit the next, I have a lot of animations. I apologize, whoever has to advance the slides. And those emissions can be temporally variable, right? And there's evidence that the temporal variability actually explains a lot of the sort of mismatch between inventories and measurements. And so we can go to the next slide. Appears to be lagging. Oh, there we go. Okay, so there are a couple knowledge gaps that we can address in part with this work and with other work in this sort of area. One is to get mass closure, right? So this figure is an example from a paper several years ago, but I think it's still relevant. Basically, that measurements of methane emissions consistently are larger than the inventories, right? And so some of that is from this temporal variability, some of it is from missing sources, right? But consistently, the inventories underpredict emissions. If we go to the next slide. And just hit advance again, so that I'll talk over that. So what emissions inventory or information is available, at least from a measurement standpoint, is really skewed towards certain parts of the natural gas infrastructure, and in particular production. And so the figure on the left is an example from some work that we did. I apologize that the reference is cut off on the bottom. This is a paper we published a few years ago showing that, and we pulled together emissions from over 1,000 individual gas wells, right? And by contrast, there are one or maybe two papers that I've been able to find that have to do with the gathering system, right? So that there's sort of the amount of information is not equal across the different parts of the industry. Next slide, please. A third one, as I've mentioned a few times now, is that the quantification of emissions over time is lacking. So a lot of the available data are from sort of snapshots, right? So either someone went and did a survey of a site, which is what the picture on the left shows, or someone did a sort of downwind tracer-based method, and that picture on the right is an example from some work that we did several years ago. But those are just snapshots, right? They're not capturing the temporal variability, and so that's something that like a stationary, continuously measuring sensor could pick up. And then next slide, please. Right, and there's still uncertainty on how best to identify leaks from this widely distributed infrastructure, right? And how to sort of implement that in a way that sort of meshes with efficient maintenance or repair schemes. And so if you go to the next slide, please. Here is a sort of schematic of the entire natural gas system. So in the top left is production, and the bottom right is end use, right? And the gathering is the part that's inside the box, where it's basically the connection between the wells and the processing plant. right? And leaks or emissions in the gathering system can occur because the pipelines leak. There can be emissions associated with specific process equipment, and then also emissions from pipeline operations. So for example, in a wet gas area where the pipelines might clog and need to be pigged to clear them out, you know, pigging the line, it requires blowing it down, and so that's an emission event. Okay, and now you can go to the next. And so some challenges in quantifying those emissions are potentially accessibility. You know, these are not necessarily on public rights of way, they might be underground. And then of course, this temporal variability piece. Next slide, please. So our approach that we're taking in this project is to use distributed low-cost sensors. And so we have a lot of experience with that. The photos on the left rather show the ramp, which is a low-cost sensing platform that we co-developed between Carnegie Mellon University and a local company called Sensevere. And this was really focused on air quality. So the photo B shows the interior of a ramp, and the sensors that are in there are mostly for pollutant gases like ozone and NO2 and carbon monoxide, and we couple that to a particulate matter sensor. And what we've done is we've been able to distribute these sensors. We've run a network in Pittsburgh since 2016. We've also deployed these sensors in Puerto Rico and in France and in several locations in sub-Saharan Africa. And so we have a lot of experience sort of in using these low-cost type sensors, using them in a distributed network. And so we're applying that knowledge in this project to this, this question of methane emissions. Next slide, please. So one example of something that we've learned with this low-cost sensor network is shown here. So if you think back to March 2020, when everyone got sent home because of the pandemic, our sensors kept running, and this was an advantage of having these continuously operating sensors. And we were actually able to detect changes in emissions that were associated with changes in people's activity, right? So one of the main things that happened when all these COVID-related closures happened is that way less people drove, and we're actually able to capture that in our air pollutant data. But sort of industrial sources were deemed, at least the ones in Pennsylvania, were mostly deemed essential businesses, and they kept operating. And so we're actually able to tease out the fact that there's a reduction in traffic and a consistent production from industrial sources. Next slide, please. So the way we implemented that in this project was to test a bunch of different sensors using different operating principles. And so a lot of them, these are all commercially available. That was our starting point. So a lot of them were metal oxide semiconductors, and a few were photoionization detectors. And so if you go to the next slide, we started with testing these in the laboratory, right? So we put together an environmental chamber where we can control what we thought would be the important parameters. So that would be the methane concentration, temperature, and relative humidity. And we measure methane. Our ground truth is with a Picaro cavity ring down methane analyzer. And we're doing all this in sort of ultra pure air. And so if you go to the next slide, what we see is that some sensors work relatively well. So the one on the left is an example of one that worked well. The sensor response, which I think is in millivolts, on the horizontal axis, and on the vertical axis is the ground truth concentration. So that sensor on the right is clearly working over a pretty wide range of concentrations. And if we were to zoom in to a low concentration range, like what we would actually see in the atmosphere, it's still working pretty well. And then that sensor on the right is clearly not working, right? That's not a coherent response. And so we did that. And if we go to the next slide, we can see that we're able to identify, we're basically able to knock out a bunch of these, right? So some of these did not work at concentrations that were relevant to what we would expect to see. And we were able to limit it to basically 3 types of metal oxide sensors. Next slide, please. However, and this is well known for all low-cost sensors, they have cross sensitivities, right? They might be sensitive to other species. They might show temperature and relative humidity responses that are sort of undesirable. And so even that, this is the same sensor I showed 2 slides ago that I said worked well, it clearly changes response with temperature and humidity. So each of the colors here is a different combination of temperature and relative humidity. And under each condition, there's clearly response, right? The sensor works under all those conditions. But for instance, the difference between the black points and the green points, which are just different in temperature and RH, is larger than the difference between sort of the lowest and the highest black point, right? And so when we go to build calibration models for these, we need to account for that. A challenge that we've learned in sort of calibrating these low-cost sensors is it is essentially impossible to recreate the full range of concentrations you get in the atmosphere in the laboratory. There's just too much sort of variation. You can't sort of synthetically, you know, make an atmosphere and have it mimic all of the variability in the real atmosphere. And so if you go to the next slide, our next set of tests, once we sort of identified what the what sensors worked well, was we adapted this so that we were sampling, we were testing the sensors in essentially doped ambient air. So instead of using clean air as our base, we're actually sucking in air from outside. Now, ambient methane concentrations sometimes are not super variable, so we can dope that ambient air with additional methane. But by doing the next set of tests that way, we do capture all this variability that we really can't reproduce. Next slide, please. And so what I'm going to show you, and I apologize the bottom's cut off a little bit, but this is a correlation matrix. Yeah, hang on, stop there, please. For different types of sensors. So it's going to be square, and the sensors we tested, we put together a unit that had sensors in triplicate. So F0s are all one type, F1s are all one type, and MQs are all one type. And the color indicates the Pearson R. So greener is higher correlation. And so what we see is if we look across sensors of the same type, they're precise, right? So all of these R's are 0.99 or 0.97 or 1, you know, it's showing that sensors of the same type respond similarly as the other sensors of the same type. And so if you advance one more time, please. There's weaker correlation when we compare across sensors. So when we compare the MQs to the F1s, you know, there's a correlation, but it's not of unity, right? It's a lower correlation, but that's sort of a feature and not a bug. That means that we can leverage data from multiple sensor types and still get information out of that, right? If across sensors, this correlation was unity, that there wouldn't be sort of value to having more than one type of sensor. And advance one more time, please. But all the sensors respond to relative humidity and temperature. So they all have a positive correlation with temperature, and they all have a negative correlation with relative humidity. But they all, you know, of course, temperature and relative humidity are anti-correlated. And so that's something we do need to account for. Now, the actual ambient methane concentrations are also slightly correlated with temperature and RH. It's a weak correlation, but it is something that we have to worry about as we go ahead and fit the data. So next slide, please. So if we do this in a naive sense, if we build a calibration model, and if what we do is we build a multilinear model that takes all of the data from all of the sensors, and we do what's called a 70-30 to train to test split. So we take all of our data, we train a model on 70% of it and test it on 30% of it. We can get really good performance. And what I'm showing here, this is the x-axis is actual concentration, the vertical axis is predicted, and we've scaled the concentration basically because then this normalizes the variables, so all the variables are on sort of a 0 to 1 scale. This was brought up in one of the presentations this morning, you know, so that we're not sort of fitting variables that have very different dynamic ranges. But if we do this naive fitting, it works great. But this is clearly going to be overfit. So if you hit advance once, it'll just sort of pop up a message, this is overfit. So if you go to the next slide, what we did then is we used some feature selection to select variables that matter, right? And so in this case, we used ElasticNet. There are other methods we could have used. And so what we find is that any of these that the ElasticNet identifies as non-zero, which are circled, are providing information. So what we really need is, even though we have 3 F0 sensors in our package, we only need 1 of them, right? Same with the F1s. We actually don't need any of the MQs to get good data out of it, and obviously we need T and RH. And so when we build a new model based on those selected features, that's on the next slide, we still get really good performance. And this actually gives us the opportunity to do a pretty tough test. Because we're only including 1 of the F0 sensors in our model, we can actually test it against the other F0 sensors and vice versa. And the same goes with the other types, with the F1s as well. Right, so we get good performance on the held out data. Next slide, please. And so this is a picture of the sensor prototype we're using right now. So at the top on that integrated circuit board is all of these sensors. Again, we're still sort of running things with triplicate sensors. We have a telemetry board in there so we can update the data in real time to a server, and then so that allows us to have remote operation of this. We can actually talk to the sensors through this telemetry board as well. So if we need to change a parameter, we can do that remotely instead of having to go out to where it'll be deployed. Next slide. And this is just showing performance of the sensor package. This is on our campus at CMU for one little brief period of a couple hours last week. You know, we're getting sort of good performance at typical ambient concentration. So we're measuring methane concentrations in the ambient of about 2 ppm, and that's what was actually there. So if we go to the next slide, I can show the predicted versus actual. Again, actual, and now it's in methane concentration in ppm is on the horizontal axis, and the predicted is on the vertical axis. And we don't have a ton of dynamic range in this particular small data set, but we're getting really good performance, right? So the sensor works, or the sensor package works. And right now we're sort of making sure that it, we're just testing out some power issues to make sure that it can run unattended on a solar panel for several days at a time without sort of, you know, running down the battery that we've connected it to. But we're getting good performance from the sensor elements themselves. Next slide, please. And so what we're going to do is what we wrote in the proposal is that we would measure emissions along pipelines and near pig launchers. And so if you bring up the first, you can bring up everything on this slide, please. We're working, our NETL partners on this project is Natalie Peckney and her group. And they've done a lot of work trying to find leaks along pipelines. So they've done sort of aerial surveys, they've done ground-based surveys with an all-terrain vehicle, and they have not really found any leaks at all. And they certainly haven't found any significant leaks. So right now we don't have any candidate locations for gathering pipelines, right? I mean, we could go put the sensor out and measure a bunch of zeros, but we haven't found any candidate locations to test it along pipelines. We do have 2 candidate locations for pig launchers where we seem like we will have site access, and that should be worked out literally in the next 2 days. And we're hopeful that we'll be able to deploy to the first pig launcher site early next week, assuming we're able to sort of work out some of these power issues we're having with our solar panel. And so if you go to the next slide, which I think is the last slide. Yeah, so just to summarize then, we've identified a sensor suite that works well, and it's measuring methane concentrations at ambient sort of levels. And we have good calibration models that allow us to invert the raw signal into methane concentration. And again, that's working at sort of typical ambient concentrations. And we will soon be able to deploy, you know, hopefully next week, near pig launchers to start quantifying the emissions using some Gaussian plume based methods. So thanks for your attention, and hopefully there are some questions.
Great, thank you, Albert. One thing I never thought I would hear in a technical presentation, and this is just because I personally, my area of expertise is not it's not natural gas related. I didn't think I'd see pig launchers in a technical presentation, but definitely something worth looking into a little more. So great presentation, Albert. I appreciate it. I'm not seeing any questions in here right now, but if you have some time to stick around, perhaps we will get some through either the chat or the questions box. I don't know what your schedule is like.
I'm going to go and have a Zoom meeting on my phone, but I'll leave this window open in case there are questions later. Yeah.
Okay, great. We'll ping you.
Okay.
Okay.
Thanks.
Appreciate it. Thank you. Okay, so we're a couple minutes ahead of schedule. I think we can still go ahead with our agenda. The last presentation of the day is with rare earth elements. Justin Richter from Penn State University will be presenting. Let's see if we can get his mic up. Justin, are you on the line? Okay, Justin is on mute. Maybe he's counting on us to start on time. In the meantime, if anyone in attendance has any questions for Albert, please feel free to submit them. Actually, I do see one just came in. Okay, Albert, are you still there? Okay, no worries. If Albert is still on by the time the REE presentation is over, we'll ask the question.
Okay, I'm here.
Hi,
Can you
Justin.
hear me? Hello,
Yes,
how
great.
are you?
Good, good. Thank you for joining us. Why don't I gave you a brief introduction, but I'll pass it over to you since it's 3:30. Why don't you go ahead and get started?
Okay, great. All right, so thank you for attending and looking forward to, I'm going to jump through a lot of information very quickly. So hopefully this goes smoothly. Anyway, my advisor on this project is Randy Vanderwall, and we also have an undergraduate student who's contributing to the research, Nick Schultz, and he's been really instrumental in making lots of progress in this work. So next slide, please.
Justin, you'll have to forgive the lag. There we go.
Okay. Okay, that went by. Okay. So this is kind of the organization of the presentation. We'll start with some directives on what's been guiding this work and what the project overview and the general workflow of this project is. And then I'll also talk about just some of the intros on what rare earths are and where they come from and how they're used, and what specific project tasks were assigned for this proposal, and then some additional supporting activities. Okay, so next slide, please. All right, so this project was really guided by the DOE NETL near-term goals that are to validate the technical and economic feasibility for production of rare earth sellable rare earth compounds from coal and coal byproducts. But this is also further supported by both Executive Order 13953, which is the resilience of rare earth supply chains for the U.S., and 14017, which is resilient supply chains in general for U.S. production, domestic production, especially for critically important domestic resources. Next slide, please. So our project really focuses on the U.S. portion of the supply chain while still recognizing that there is a global supply chain for rare earths and critical minerals. And this is to say that the assumption of the U.S. domestic production side, coal and coal byproduct separation and concentrating, is and will be in effect based on the production with NETL's funded research. And so we'll look at imports and exports and the importance to the U.S. supply chain, but really we'll focus on the refined oxide metals and the sintered products, final products, and end of life and disposal. And that's kind of the main capture we're going after here to define those markets and demand drivers. Next slide, please. So the general workflow kind of starts with a lot of literature search and collection and refining, and then extraction by keyword and compilation via OneNote, especially taking notes and combining imagery, figures, extracting data tables. And a lot of the compiling figures and data tables has to do with web data extraction, because sometimes data is not readily accessible, especially when it comes to immediate term market pricing and imports and export of goods. So we identify gaps based on all this information we collect, and then we keep going back to the drawing board, pulling out more literature and information. And then as we gather this information, we start assigning it to the specific tasks for the funded project. And then in the end, we come out with a summary for each task and how far we've accomplished and how much more we have to go. Next slide, please. So in reality, rare earth are called rare earth because they're difficult to extract, not that they're rare in the earth. And this is kind of a misnomer. So that was a little bit of an eye-opening experience, because really calling them what they are is not accurate here. So they could be called complicated to extract minerals instead. But these are essentially the 17 scandium, yttrium, and the lanthanide series elements that are really the most difficult to extract, and the uses are as we'll see slightly later in the presentation, they're pretty crucially important to technology across the entire United States. We also look at the rest of the critical minerals that are defined by NETL, but this was actually an administrative assignment by Congress to define the 37 critical elements and critical minerals and rare earth elements. And so, next slide, forward it, please. The deposits are actually pretty prevalent across the entire globe. So they're accessible, they're available. Unfortunately, they're very difficult to refine and process. And so the majority of the refining and processing happens in China. Next slide, please. Is it possible to advance the slide?
Yeah, this transition appears to be frozen. Justin, Solly, you may have to stop. Yeah, there you go. He's going to reshare his screen.
Okay, thank you. Okay, so we'll start right into the project tasks. And the first one is essentially to identify industrial opportunities where rare earths and rare earth containing materials would and could be used if a domestic supply was available. And so the prior work identified that roughly 59% of the rare earths in the US were used in mature markets, catalysts, glass making, lighting, and metallurgy, where the remaining are in the newer, higher growth markets, especially in batteries, ceramics, permanent magnets, and energy. And interestingly, it's used in laser sighting for a lot of critical national defense applications as well. And so we prioritized rare earth elements and critical minerals used in electrification because these are really the high growth demand markets. And if you participated in the Pittsburgh Coal Conference last week or the week prior, you see that there were at least 3 other presentations that also referenced that electrification is, for at least the near term, driving immediate demand for rare earth elements. And so lithium and graphite are particularly critical to these areas, especially for energy storage. But neodymium, dysprosium, yttrium, praseodymium, samarium, europium, and terbium are used in permanent magnets and renewable energy. And these are also growing in crucial importance too. So the next quarter of work will address the long-term future demand markets, what it looks like for a potential 20 to 30 years out the road. Next slide, please. So I want to review some of the uses of these materials, and this came out of a Nettle infographic. It's a really fantastic piece. It's showing that mature markets consume roughly 60% of it, and 50% in the global markets. And typically lanthanum and cerium constitute about 80% of that 60% or 50%. And so the newer high growth markets really are driving the remaining. And it's only really 3 elements. It's dysprosium, neodymium, and praseodymium. And that's about 85% of the newer high growth markets. Next slide, please. And so, as we say, these demand drivers are really electrified. Electrification is shifting consumption to really a more mineral intensive system. Next slide, advance, please. And so what we see is that in 2010, we're just kind of putting a reference out there. In 2010, the US clean energy demand was a small portion of the total energy demand of the entire world. But that in 15 years time, that has expanded substantially. And the minerals used in selected energy technologies in the top right for electric vehicles compared to a conventional car are anywhere between 5 to 10x the quantity of critical minerals or rare earth elements. And in power generation, that's seen even further. So for coal and natural gas, it's low weight of minerals per megawatt produced, but wind, especially offshore wind, as they grow and expand and get even taller, they're requiring more and more metals, especially rare earths, praseodymium, dysprosium, and neodymium for the permanent magnets in their generators. Next slide, please. I apologize, I seem to be having some problems with transitions. Okay, so there's many projections out there, and all of them point to the growth in wind turbines in total size. As they expand and get larger and larger, these minerals are in higher and higher demand. So 2015 we had 9 megawatt was a standard offshore, and now they're moving up to the 11 to the 13 to 15 megawatt range, and these are enormous machines requiring a significant amount of rare earth elements. And so as new installations continue to increase, and as the offshore capacity of the United States has been opened, there's just further expansion potential for wind generation, which requires greater production of rare earth elements. Next slide, please. All right, so electric vehicles are the secondary market for this expansion of electrification and consumption. So the difference between rare earth elements in internal combustion engines and hybrid, just even hybrid vehicles, is roughly 10x. And that's kind of interesting because as we expand to producing more and more hybrid electric, as that's growing the market segment for all electric vehicles, plug-in hybrids are hot on the tail of that, and further behind that are battery electric vehicles for range especially. And as this expansion of electric vehicles of all different varieties grows across the world, hence also grows the requirement for critical minerals, lithium, cobalt, graphite, and rare earth elements used in generators. And next slide, please. So Project Task 2 is essentially to identify current industries and companies that utilize rare earths within their supply chain and where these opportunities are located. So there are really few US manufacturers identified. We're still working on this. This is a kind of a work in progress because it's not really advertised that many companies use rare earth elements in their products. So this is more of a detective game for us. We're diving deeper into the individual products and then tracing those products from the shore to where the particular companies that manufacture them or make them in the US. And so we have to understand what the broader domestic network of inputs and outputs of these materials are. Next slide, please. Okay, so task 3 is we want to understand what the global resources for these critical minerals are, where they're located, and what the processing looks like for all of the 37 critical minerals. This is a big ask, and so we've focused really on the electrification portion of things because, again, across many other presentations, we've seen that electrification is driving demand. And so those minerals that are used in electrification are really the ones that we're going to be putting a lot of heavy emphasis on. And so the current work is really evaluating the USGS mineral commodity summaries from current all the way to the past 2 decades. And then there are accompanying market analysis reports that show really good coverage of rare earth element production across the globe. Now we're also looking at global input-output economic models, and these, while they're generalizations of inflows and outflows of economy, they have a really good identification of dollar amount flowing from one country to another, and so that can be mapped to product categorization and rare earth elements within products. And so what we find is that the rare earth reserves in China are kind of at the highest, and Brazil, Vietnam, and Russia are also very, very high up there. The US has a significant amount of reserves, and more of them are coming available each and every day. And we're identifying more and more of them every day. I met with the USGS, and they're pretty hopeful that a significant amount of further resources will be identified. And in parallel to this, a proposal was just approved to identify lithium extraction in northern Nevada. And so we're finding other resources across the US. Next slide, please. Okay, so as we talked about, China has a significant amount of resources. They also dominate the global production of these minerals. And so for the last 20 to 30 years, China has been dominating the global production. And it was a very strategic and very intentional pursuit from 1988 on. And they've had roughly 90% of the global production since then. And recently, with understanding, there's been a push for a China-free supply chain, and this includes U.S., Japan, Australia, sometimes the European market, and these countries are cohorting to figure out production to reduce the amount of requirement on Chinese demand or Chinese production. And so that's reduced the total global production to about 62% for China. But China is really doing some strategic domestic stockpiling at the moment to figure out how to manipulate the market. And we need to be very well aware of this in the US, as this is a domestic hindrance. Okay, next slide, please. So task 4 is to look at the historical perspective of all of these minerals and to understand what it looks like since about 2000 and what the market potential for the US domestic production through 2035, but also what could potentially be the import reliance on these materials too. And so if we have partner countries that we can build a network with, a supply chain network with, as opposed to potentially conflicting markets or conflicting partners, we see an opportunity there for interesting governmental partnerships in production of these materials. So we want to prioritize demand driving markets in the short term. This is really, really important because the short term is what is going to make or break a lot of the US domestic supply chain. And so adding in Q3, what's upcoming, we're looking at the long-term and future demand markets for this. And so we looked at historic market reports, pricing trends, and commodity summaries. And we're starting to extract more and more pricing commodity summaries from as far back as we can reach. Okay, so next slide, please. So the historic pricing trends, this is just a snapshot of what happened over the last year for selected minerals, rare earths in particular, that are used in the permanent magnet supply chain. And so what we see is the prices continually increase over time. And sometimes there's jumps, sometimes there's little hiccups, and sometimes there's relative stability. But as we see that terbium is starting to be, it's expensive, one, because it's in really low quantity when it comes to extraction, but also it has high value for its mechanical properties. And neodymium and dysprosium are still very in high demand, although their prices are relatively stable. So we want to show this over a longer period of time and use that assessment to predict what pricing could look like with different production scenarios in the US. Next slide, please. Okay, so as we said before, the US is really heavily import reliant. Although we have a significant amount of minerals that we use in the critical mineral list, we don't produce roughly 22 of the 37, and we only have byproduct production of roughly 5 of them. But we have domestic partners and partner countries that have a really good production that we can lean on to gain access to. But for the rare earths, that is extremely limited, and they're non-market economies. Particularly China are heavy on the yttrium and lanthanide series rare earths, and so we have to figure out a bit of a liberated supply chain from non-market economy countries. And the US and Australia are really pushing forward on this agenda. Next slide, please. Okay, so while it's heavily import reliant, we can see that back in 1954 we had very limited requirement of imported materials, but as of 2019, that number just blossomed, and the quantity of material that we're requiring from import sources is significantly expanded. And so because we have minimal US domestic production of any of these minerals, we found that refining is really capital cost intensive, and the countries that have the refining capacity are really using that to their advantage. And this is especially true in China because they have a favorable pricing strategies where there's an FOB price, which is the global production price. They show to the world that anybody can buy at this price. And then they have a domestic price, which is an incentive for domestic producers to take the rare earths and rare earth oxides, refined minerals, and turn them into a secondary product. And those secondary products are usually, they have no VAT, no taxes, import taxes in most, in either the EU, Canada, the US, or any developed countries that require import of those permanent magnets or secondary products. And so China has a significant incentive to keep the materials in-house for production because there's no taxation on the development side. And so there's none of this. Nothing like this happens in the US. Nothing like this exists in the US. And so we intend to provide some sort of strategy to describe what is happening. Next slide, please. Task 5 is to identify the most imported products in the US that contain critical minerals. This is really challenging because the data is all over the place. And so there's imports and border control. There's some really interesting data coming out of there at the port level. So values in as far as dollars go and finished products. And then we're also data mining the US Census Bureau and the Bureau of Economic Activity, or Bureau of Economic Analysis, excuse me, for end-use imports and micro-level trade in goods and services. So the data really is in this current state of just messy Legos. And we're working on Q3 to be sorting and arranging and to present them in a way that makes sense so that there's some takeaways from this and that it can be used to describe and to inform policy. Next slide, please. So some of the interesting uses that we found, especially for final products, are across all different industries. Defense is really interesting for lots of rare earths and critical minerals, especially the rare earths. And so all the industries on the right have different products, final products, and intermediate uses. And so what we're really interested, we're finding that the US primarily consumes the light rare earth elements, where the heavies are only about 2% of domestic consumption. But we still want to map out what that looks like for future production, and that's all a part of Task 5. Next slide, please. Okay, Task 6. So this is more of a global statement where we look at what is it, where are the resources located, and quantify with all of the 37 minerals where they're produced in the US, and if production could reach capacity where we could eventually turn it to export, what does that look like? So we started work with the materials flow through industry tool from NREL, and they have a database to enhance rare earth data and flow through industry products. And so on the right-hand side, this is kind of a reporting scheme that they have for individual materials. And this is acid roasting of moissanite, bastanite, and this is where a lot of the rare earths come from, the clays. So this kind of information tool is possibly a strategy that we will implement to export or deliver some of the data. We're still working on what the credentials will look like and what the pages will look like, but this is something interesting we may propose as we go forward. And so we're also looking at this using the input-output models, economic models, global production and global consumption, where structural path analysis is an economic tool to trace what materials flow through what particular industries. And so that's part of the Q3 to Q4 task list of Task 6. Next slide, please. So in the US, there's a substantial amount of rare earth resources available, and some of the older mines are being revived and some of the newer mines are being found. And just recently, Northern Nevada, Texas, and even near Atlanta, Georgia, there are international partners moving in to help with the refining of minerals found in the specific areas. And so there's development happening, and it's happening very quickly. So the next stage of our work also will include, I say, extracting information from the newspapers and the tabloids, because that's where activity is happening very aggressively and very quickly, and things change very fast. And so we will use that as a source of our prediction for the next stages. Next slide, please. I apologize, my transitions are heavy. It seems like my presentation is, I used high resolution images. Ah, great. Okay, so the final task we have is to identify industrial opportunity for utilizing critical mineral containing materials within the US. If, as Nettle produces rare earths and critical minerals from coal and coal byproducts, where they could be used to ensure that critical minerals remain within the US. So this is kind of the circularity focus of the work, to identify where these materials can be extracted, processed, refined, and recovered at the end of life. And so there's still more work to be done on replaceability, understanding what these materials look like, and we will revisit demand driving markets. But the idea, Honda promoted their first electric motor that's rare earth free, and MAL and Turntide Technologies in the US are also looking at rare earth free generators, energy generators and motors, but Tesla has decided that they're not pursuing that route at all. So they're still, electric vehicles are still really driving the demand for rare earths as well. And so the task 7 really is pending the completion of task 2 and 5. So as we move further on each slide, task 7 will kind of fall into place. Next slide, please. So some of the additional supporting activities we've done, we've created a research collaboration with my dissertation committee as they worked in rare earth elements and extraction of rare earths. And so they have a substantial network of rare earth and critical mineral partners, and especially in their research. So like I said earlier, we have a proposal in development for lithium production, and then we signed on an undergraduate researcher, and that's some of the work we're mentoring right now. Next slide, please. And so as you know, this is part of the requirement. We acknowledge DOE and Nettle for and the UCFER project for funding this study. It's been an exploration in a very interesting path. So we thank you. And next slide, and open it to any questions.
Perfect. Thank you so much. We actually did have a question come in. I got a sorry, I lost my question box.
Sure.
So this is a pretty important comment.
Sure.
From Shamlal Madhava. He's the technical point of contact for UCFER at NETL.
Okay.
He said you might consider talking to Dr. Kelly Rose. So
Okay.
she is the technical director at SAMI, which stands for Science-Based Artificial Intelligence and Machine Learning Institute at NETL.
Okay.
You might want to get in touch with her to see whether you can leverage search data and geospatial tools that we develop. I think
that would be great.
That may be useful here. Yeah, it's Dr. Kelly Rose.
Okay, is it possible to email me that information? That would be extremely helpful.
Sure, no problem.
So I didn't also state, but I made connections with USGS, and they have a statistical research group, and the leader of the rare earth commodities is Joe Gambogi. And so we've made some connection on identifying some of the path forward on each one of these tasks, because he's the rare earth commodity expert of the entire US. So we've been gaining support external, because there's some really great research going on out there.
Yeah, absolutely. So I will send you information on Kelly Rose, and I will copy Sham in case he has anything to add.
Great. Thank
Sham,
you.
was there any follow-up to that comment that you would like to add on to? I apologize. I didn't check to see if it was on.
Thanks, Omar. Nice presentation, Justin. Nothing more to add, but he has also looked at I think minerals, maybe perhaps related to rare earth elements in core minerals. So she might be able to help you with tools that her university developed. So you might chat with.
That's great. Thank you so much for that. That's very exciting. I'm kind of a data mining nerd, and so I'm very much into geospatial mapping. So that would be a really great partnership.
Perfect. So you'll have to remind, it's Gavin Pickenpaw who is your RIC point of contact for this subaward,
Yes, sir.
correct?
Yes, sir. That's
Okay.
correct.
Okay, so I'll have him make the connection since they're both in the Research and Innovation Center.
Great. Thank you so much.
Yeah, of course. So there was another question. Well,
Sure.
okay, so while we're still on this presentation, this was more of a passing curiosity as you were talking about, global supply chains with critical minerals and how they, early on in your presentation, you talked about their relation to wind turbine construction.
Yes.
And
Yes.
it reminded me of this news article I saw with Norway building what they say will be the largest offshore wind farm ever.
Yes. Yes.
And as I'm sure you're familiar, and do you know, I don't know if this is superfluous to this specific project, but could you maybe talk about our involvement, if the US has any specific involvement in that development, or?
As far as I know, I can't speak to what the U.S. involvement is, but I do know that typically up in that area, Vestas and Gamesa are the large heavy-hitting wind turbine manufacturers in that area, and GE typically does not have the international clout for wind turbine production, as do Vestas and Gamesa. So I can't say for certain whether the U.S. is involved, but I can definitely explore that and get back to you if that'd be all right.
I mean, it just reads to me as a big supply chain case study.
Oh, for sure.
So yeah, so I'm okay, yeah, and I know that you're talking about it a lot in the sub-award, and you're exploring supply chain issues with Core CM, so it would be interesting to know. Obviously, don't do more work than you have to. But
well, it's definitely an interesting case study, and it's one that it's relevant because it's immediate.
Right, short term, immediate. Yep. Okay, so I didn't want to lose sight of another question that Sham posted. So, well, thank you very much, Justin. I'm actually going to get into a question that was directed towards Al Presto. Al, are you still on?
Yes.
Great. So we had another question with your presentation. We can get his slides pulled up just in case. Do you need to account for ambient conditions like wind, rain, etc., to quantify methane emissions? CH4 emissions?
Yeah, and I didn't sort of explicitly lay out how we're going to do the quantification, but yeah, you need wind speed and direction, which we didn't, sort of build directly into this sensor. The sort of setup is mainly for methane. Mainly because we already have some anemometers that we have rigged up for a previous project that we can use as they are. So yeah, when we deploy, there will be an anemometer on site, so we can have wind speed and direction.
Okay, great. All right. I guess, well, it's 4:03, and this Q&A is supposed to end at 4, but we had some good discussion going. If anyone has any follow-up questions, all of the presentations will be posted on the NETL conference proceedings page, the official link. Once we get everything on there, I think there are a couple presentations waiting to be uploaded. But once we get all the presentations on there, Penn State or Bruce, you guys will send out just a debriefing link, so to speak, with that conference proceedings link included. So if you guys have any questions or want to reach out to any of the PIs directly, please do so. All of this information is publicly available, and everyone who presented was obviously very invested in the research and very interested, and would welcome the opportunity to answer any follow-up questions. So I would like to thank all of those who presented today. Very interesting stuff. We will definitely send out the links so everyone can access the presentations at a later time. Additionally, we will also have a recording of this webinar for both days available on NETL's YouTube channel, I believe. So once all of that information is gathered, or we'll send it in an email out to all the attendees. So Bruce, I'm going to pass it over to you because you also had some closing remarks.
Yes, thank you, Omar. Yeah, I too want to thank all the speakers from today as well as yesterday. I thought this was a very informative meeting. I'd also like to acknowledge all the PIs and researchers for these, excellent projects. And before we leave, I wanted to acknowledge the NETL team. We work with Omar and Lauren on a regular basis, and they're a pleasure to work with. Justin, he's done a good job as IT support for our virtual meetings. This was the second year we've done it virtually, and while we may have had a few glitches this year, this is just the nature of remote meetings, teaching, work. Overall, I thought this meeting went well. And then as I learned yesterday, Sham and Karen Blaney, they need acknowledging for work they've done behind the scenes. I also want to acknowledge my Penn State support team. Jennifer Matthews and Elizabeth Wood are my two right-hand persons. All of you have received and will continue to receive correspondence from them. You also receive emails from Heather Harpster. She tracks reports for me and sends you reminders, that reports are soon due and sometimes when they're delinquent. And then from the contracts and invoicing side, I want to acknowledge Jennifer Lear and Kelly Rhodes. Without assistance from this team, I wouldn't be able to keep UCFER's train on the tracks. And then, finally, I hope that next year we will be able to meet in person, as I've not had the chance to meet most of you. With that, I'll turn this back to Omar.
Thank you, Bruce. Thank you for the kind words. And I just want to echo that, yes, I do hope next year will be in person. Who's to say? I know that there were so many new additions to the NETL staff that I too, when I come back to the lab, won't be able to recognize very many people. At the same time, I think this arrangement, the annual review meetings, are best done in person. That way you can have some FaceTime with the people you're collaborating with. So hopefully, fingers crossed, let's see what happens. In the meantime, we'll do our best with tracking your accomplishments. If you have any accomplishments that you would like to send to your task monitors or in writing to your RIC POCs, please do so. I don't think a whole lot of NETL upper management was able to make it over these 2 days, but that isn't to say they aren't interested in relevant and meaningful progress under these subawards. So please, if you get the time, please send the accomplishments to either your task monitors or your RIC points of contact, and then they'll move it up the chain. We definitely want to maximize the visibility of these subawards, and it really starts with the PIs communicating all of the important highlights of what they researched. So again, to close, thank you all for your attendance. This was a great meeting. We will send out all of the necessary information, all of the follow-up information in the coming days once we're able to compile all of it. So with that, we're going to go ahead and adjourn. Thank you, everyone. Enjoy the rest of your evening. Take care. And Lauren and Justin, we can stay on just for a bit. And Bruce, if you're willing. No, Bruce is off.
Thank you, Beth.
Oh, well. Okay. Good meeting, guys. Lag, nothing we can do. It is what it is. Wait, sorry, we got one more.
You're good.
Okay.
Yeah,
So
there's definitely nothing done about that.